also running the fourth workshop on neural architecture search. Thank you very much for attending. What's the next bit? I've seen these slides beforehand. So this year we have an introduction to NAS. So last year we had a lot of people who said that they didn't feel as though there was a lot of talk about what NAS actually was at the start. So we're going to give you an introduction to NAS, which is hopefully useful information if you're not fully aware of it. And if you are aware of it, hopefully at least you'll find something new in it. Then we've got Frank Hutter is going to do a talk, for a keynote speech for us just after lunch. If you know Frank or have heard of Frank, he's a very highly important figure within the actual neural architecture search in the AutoML community. We've got 8 great papers that have been accepted. And we'll also have the results of the 3rd Unseen Data Neural Architecture Search competition, which finally finished, I think it was yesterday almost. So really pleased with that. So we've got 2 things here. So this is mostly for the people who are actually online, or it can be for you guys as well. We've got a mailing list if you want to join our mailing list to find about future events. And we've also got an online form, which is the same as the paper form I've just handed round. And that's for people who are either online or for people who are in this room and they don't want to actually fill in the paper form. But feel free to join the mailing list or fill in the form. That would be great. Actually, I think some people are still trying to grab that screen.
Sorry, go back.
Yeah, watch the cameras. It's not just your gorgeous looks they're trying to capture, Brilliant, brilliant. Okay. So the schedule is fairly straightforward. We've got a couple more minutes before we'll actually do an introduction to NAS. We've got a coffee break, which I don't know where it is yet because this is the first day, but I'm guessing somewhere out there we'll find some coffee and hopefully something to nibble on. After the coffee break, we've got the first 2 papers. Do we have any of the authors for the first 2 papers around the moment? Well, hopefully they will turn up before the coffee break.
Some of them are online.
Oh, some of them are online. Brilliant. We'll talk about the competition and the results we got from the competition. We'll have lunch. Again, I don't know where lunch is, but presumably it's around somewhere. Frank's going to do his talk in the afternoon. We'll go through some of the other papers. And then finally, at somewhere around 5:30, we'll actually conclude the event for the day. But we're more than happy to chat with people at any point during the day about anything they want to know about. And as usual, it's taken far less than the 10 minutes I allocated for me to say hello and welcome. So David, I don't know if you want to take it away with the...
Yeah. Okay. So as Steve said, we last year we found that a lot of people at least came to the morning session were wanting to see what NAS was about, and we're kind of through into the deep end. We're straight into, I think it was one of our talks, which was a bit more dense than someone who's new. So we wanted to do a introduction talk so that everyone's on the same page. And to that extent, we're going to start with a brief introduction to what a neural network is. Now I know this is CVPR, so I think most of us have a very good idea, but just to make sure we're all on the same page, and for anyone who is extremely new, we're going to talk about how to determine the best network, the challenges of finding the best network using traditional machine learning, how NAS can be a solution to this, how challenges have been addressed in how NAS has addressed these challenges, and the current challenges for research into neural architecture search. So first, what is a neural network, as I said? So a neural network is basically a collection of layers and nodes, like from the simplest sense. So you start with an input layer, you have multiple hidden layers, which is where a lot of the magic happens, and then you have an output layer. And these layers are connected via edges from nodes to nodes. And in a very traditional sense of a network, you have this kind of fully connected mesh. Now, so we take a closer look at a node. So we take a look at the bottom one. it takes in inputs from the previous nodes in the previous layer, and they each have a weight associated with them. And so the node sums together the weights, the inputs from the previous layers with respect to the weights. So the weights kind of modify how strong each edge is coming into the node. So that's all summed together, and then we have an activation function which is applied to this, and it can either be sigmoid or relu or any other activation function, and that gets sent out to the next layer. So in this case, it would be to the output layer. So moving on from just a regular neural network, because that is a very traditional sense of what a neural network is, and they've gotten a lot bigger. So this is GoogleNet, which is a form of inception. And you can see to fit on the screen, it has been rotated and it is a lot bigger. So one of the reasons that we wanted to bring up this one in particular, although ResNet and other networks also shared this feature, is Inception uses Inception modules. And so you can see throughout GoogleNet, you have these similar blocks of features that are together, which are essentially just that module at the bottom replicated throughout the network. Because this pattern of having these replicated modules throughout your network was inspiration to use cell-based networks. So a cell-based network is a much smaller network. So rather than having layers upon layers upon layers that you have to search and train, instead you have a very small network. So in this case, from the example, there's only 4 nodes with about 5 connections. And they're chained together to build your bigger network. So it's instead of having to search for a big network, you just search for a small one, and then you just repeat it. So we'll get onto this in a bit later, but many NAS methods use cell-based architectures because it reduces the scope of the search. So we'll talk about a neural network, and so how do we optimize a neural network? Well, so first we need to decide what we're optimizing, and usually that's accuracy, but it's not always. But a lot of the time, especially in papers, they will tend to report the accuracy of a network on a certain data set. So every problem is different. So I don't know, for example, Cipher10, which is a common data set, you might get better accuracy if you put more convolutional layers in, but compared to the other networks, but you might get better results using more pooling layers on a different data set, because there's no one network fits all. We also have to consider the hyperparameters. Changing the hyperparameters can drastically affect on how performant the final network is. And so it's all well and good to say, oh, I've created the optimal network for Cipher10, but you've only used a fixed set of hyperparameters because you haven't actually fully explored the search space. And you can also include data augmentation in this process. A lot of networks perform better once you either use data augmentation to get more data or to obfuscate like cheating details. For example, on a photo, if you're grading photos by year, your network might figure out how old the photo is based on the grain rather than the actual contents of the photo. And so you could use a blur for data augmentation across all your photos in order to try and reduce the impact that the photo grain would have. So as I said, finding the best network, we have to determine what we're optimizing for, because it's not always accuracy. And once we've decided that what we are optimizing for, we need to find the network that's as optimized as possible. The only way to know for certain is to try every network, every combination of data augmentation and hyperparameters. Because as I said, they all can have a very big impact, and so even a small change could mean drastically different results. A brute force approach would be required here to find the true solution. However, the size of this problem is quite large. So the number of nodes and layers is almost infinite. You're only limited there by the size of your GPU or your TPU or whatever device you're using to train your network. Similarly, the number of connections between your nodes/layers is all this is limited on the memory of your GPU. Currently, there are a lot of different types of operations that are used. So you've got your convolutional layers, you've got your batch normalization, you've got your max poolings. There are obviously more that people have yet to develop, which might be useful. There are probably so much have been forgone to time. In the grand search space, all of these need to be accounted for because, as I said, every problem is different. And so some operations are going to perform better than others. And hyperparameters. So every combination of batch size, number of epochs, the learning rate, the optimizer that you're using, all this can have a major effect. And this just keeps adding to the problem exponentially. So what we traditionally do in NAS and what we're going to do here to try and talk about how to optimize the best network is we create a search space. So we're going to hold off hyperparameter optimization until we've chosen a final network. This is quite common in a lot of NAS methods. So we're going to limit our search space to a cell-based network, and to build that cell, we're going to start with 4 nodes. And between all these 4 nodes, we're going to have 6 connections, and we're going to have a candidate operation list of a 0-wise layer, skip connect, 1x1 convolution, 3x3 convolution, and 3x3 average pooling. And we're going to color code these. So this is all the networks that we're going to consider. So we've gone from infinite to a somewhat restrictive space. It's still going to take quite a long time to train. There are 15,625 candidate architectures from just that small restricted space. And if you train 1 an hour, that would take about 2 years. Now, hopefully we'd be able to do it quicker than that, but this still take a long time. So we want a method to reduce the amount of training that's required. So a question that we have is there a shortcut? There are 15,625 different cells, but each edge only has 5 possibilities. So if we look at these 2 cells, if we calculate for weights of a 1x1 convolution on the edge pointed out there on that cell, is it possible to use those weights on that same 1x1 convolutional edge on a different cell? If we can, we actually only then need to train 30 total edges, and then we can go back and get our weights, and then we've trained our effective whole search space. And this is kind of a form of NAS. Because we created a search space of candidate architectures, and we implemented a method to try and quickly search through them and find what we consider the best one. So the network topology that I used is based off of the NAS bench 201 / the NATS bench search space, which contains those 15,625 architectures. And the weight sharing method to reduce the runtime was inspired by NAS. NAS is a form of NAS which uses weight sharing to massively reduce the time taken over the original NAS method, which we'll talk about in a minute. So there are 3 parts of a NAS algorithm. So there is the search space. So this is all the possible networks that your algorithm can consider, and this is an important part of NAS. If you have a really good search space, you'll get a really good result, no matter how good your NAS method actually is. Then we have the search policy. So this is the actual algorithm itself. So this is algorithms like the original NAS, like ENAS, like DARTS, etc. And the search policy is made up of 2 phases. The search phase, which is where you actually find the architectures, and the evaluation phase, which is where the architectures are trained and tested. Then finally, there's the data policy. As I mentioned earlier, data augmentation can have a very big effect into how performant a network is. And so you need to take into account what type of augmentation that you are using. Good augmentation can lead to more data or can lead to better represented data. So I'm going to briefly talk about the original neural architecture search algorithm for people that are possibly new. So softly, with the original neural architecture search via reinforcement learning, realized that neural networks could be written as strings. You can encode a network as a tokenized sequence effectively and then represent that as a string. Therefore, you can use a recurrent neural network, a network that's better designed for text generation, to generate these networks, either CNN or RNN networks. Using the validation actually as a reward signal, we can use reinforcement learning to generate child networks. So the process of NAS, it would generate a network, train it, get its validation accuracy, use that to update the controller would use that to generate a new one, and this would repeat. The original NAS took way too long. The original experiments took between 21 to 28 days using 800 GPU or 537,600 GPU hours, which is about 61 GPU years. Now, I believe that these people were working at Google Brain at the time, so it's no surprise that they had access to 800 GPUs, but not everyone does. In later experiments, they extended their work into NASnet. This is when NAS, I believe, started using cells. They massively reduced their search space from looking for a full network to looking to a cell, which they would then repeat. This reduced the search time significantly. It went from 800 GPUs over 28 days to, I believe, only about 8 GPUs running for about a week. I can't remember it off the top of my head, but it was, it says here 4 days of work on 500 GPUs, which is about 43,200 GPU hours, which is about 5 years, which is a significant difference in time, but it's still too long. In the real world, if I went to my boss or someone and said, oh, I can get you a network that's good in this, but it'll take 5 years, I don't think I'd get approval for that project. So this is still a long time, and so other work subsequently, our main focus was reducing the time taken for NAS to perform. So one of the techniques they use for that is weight sharing. And so in the example we used before, it was inspired by ENAS. And so ENAS, they represent their entire search space as a directed acyclic graph, where every network is a subset of this big graph. And while training, if they have an operation between nodes that's trained, that's been trained, they'll go back and get back those weights, so they don't need to train them. And this means that as you train more and more candidates, eventually you train all your possible operations between each node, which means that training the final network is much quicker, as eventually you'll have all the edges trained, so it'll just be grabbing the weights and doing a quick run through. So the idea is to reduce the amount of training required by sharing the weights between the architectures. So as I mentioned, ENAS does this, but several others do as well. Darts uses a form where they represent all their operations as a continuous space and use bi-level optimization to figure out what the final operation should be. And usually in these methods, once the final network has been found after the training method, they retrain the final method from scratch and retrain all the weights. So the final network does get fully trained. So there are a few problems with weight sharing. So the speedup comes with a performance trade-off. So Yu et al. In 2019 found that weight sharing was detrimental to performance. The image that you can see on the right is from experiments done on a very constrained search space for RNNs. They used 32 architectures, got the ground truth of each architecture of how well it performed, and ranked them accordingly. They found that when ENAS was applied to this search space, none of the found architectures were in the correct ranking position. So the diagram on the right, so the colored section, the numbers in each box represent the disparity. So as you can see with the red arrow, the architecture which was ranked ground truth at 6 was picked first. This was picked as the top ranked. So there are 5 ranks of displacement. The worst of this, I think, was the one that says 17. When in a search space of only 32 architectures, that's almost half. So that is quite a big disparity. In their paper, they also found that by removing the weight sharing from ENAS and NAO, they found better architectures. NAS increased by 92,329 ranks in their CNN experiments. And as I said, in their experiments, weight sharing never produced a true ranking of an architecture. And another method that they try to use to reduce the amount of time that NAS takes is performance prediction. So weight sharing reduces the amount of training that we have to do, but what if we can remove it at all? So performance prediction is the idea of using an encoding of an architecture and estimating the performance of our training, usually by using some sort of model. So a common form is to use a sort of neural network where you use the accuracy of the accuracy of a few trained models to generate the network, and then you can feed in a new algorithm and get a new guess of how performant it is. So a problem with predictors is there is a trade-off between the query time and the initialization. So performance prediction for the low query time. So this is the time that when you give it a new network, how quick you get your response back. They often require hundreds of pre-trained networks for training data. So you need to go and train all those networks to build your data set, to build your model that will encode. So that can give quite a large initialization time. So if you're training, if each network trains in about an hour, that's 100 hours, which isn't anything like what the original NAS was, but it is still a consideration that you need to take into account. And on the other side, predictors with low initialization time, so you don't need to train that many models, they actually tend to have a longer query time, which mitigates the main benefit of performance predictors. It's still a good speed up, but it's just not as good as when you have the larger initialization time. But these are things that you have to factor. There's also questions about how accurate they are. So you will get a lot of performance predictors with good accuracy, but as it is a neural network and therefore a model, it's not 100%. So although it will predict you probably a very good algorithm, it's not necessarily going to predict you the best one. And if you need the best ones, you probably can't justify just using a prediction. So you might need, so you would have, if you need the best one, you'd have to go find another method. So from both these options, the question is there a good option? Well, so everything is a trade-off. While weight sharing and performance prediction won't necessarily find the best network, they do often come close. They do often give very high accuracy. And most of the issues mentioned on older NAS models, which had other problems, including the search spaces, which we'll touch on in a moment. Newer approaches attempt to alleviate some of these issues. Boss NAS, for example, doesn't share weights across the entire network like ENAS does. It uses small blocks which it uses to build up its network, and only weight shares inside those blocks. So it really does depend. If you don't need the absolute best architecture, but you need something relatively quickly, but it just has to be good, there's no need to go for the best. So you don't need to do a brute force approach. You don't need to use some of these algorithms that longer. You can take this trade-off of a bit of a loss in accuracy for the speed of training. But as I said, as I mentioned, some of the issues of older NAS models was their search spaces. So Yu et al. Again found that search spaces that were used in the earlier NAS methods were too restricted. Effectively, all the architectures in them were pretty good. They generally were above 80% in accuracy, if I remember correctly off the top of my head. And a lot of the methods didn't actually significantly outperform random search. So random search, you wouldn't expect it to be getting very good accuracy in comparison to methods that are designed to try and find the best network. But in Yu et al.'s experiments, there wasn't that great difference between the methods found, the architectures found with random search versus the architectures that found via the NAS. And in some cases, the random search actually outperformed NAS. NAO, specifically in their experiments, often performed lower than their random search during their experiments. to actually know whether your architecture is good or your algorithm to find architectures is good, you need a search space which has the bad networks and can figure out that they are bad. So you're out in the same paper, they also found that many NAS methods use the results of the evaluation phase to justify work in the search phase. So a lot of the work in NAS is searching for the network rather than the final evaluation. But we use the final accuracy of the final trained model as justification for our approaches. For example, when you look at benchmark indicators for like ENAS or NAS or DARTs, you will see their final cipher 10 or ImageNet accuracy. But that does not necessarily, without having the ground truth of what is actually good, it really doesn't make sense. In your search space, you could have a model which gives you 100% accuracy and or 99% accuracy on ImageNet, and your method returns 91%. Now, 91% is a good result, but from your search space, it's not actually that good because you're on the lower end and it's 99. So we need to actually understand how good the search space is, how good it can be, and how well your algorithm works inside those constraints. So the solutions to the issue that we have with the search spaces and the search phase is these are standard benchmark search spaces. If the search space is the same, the results between methods is now directly comparable. We can say that it's not the search space that gave you the results. It is your method has found a better architecture than the others. The NAS benchmarks are fully trained, which allows you to evaluate the results based on the ranking rather than the raw performance. A lot of the algorithms on the NAS benchmarks are within less than 1%, but we can actually have a look and see how well each of the architectures individually ranks to see how well they are in comparison to each other. A common search space is good for comparison and testing. However, a search space may not include good architectures for a certain problem, as we talked about earlier with like hyperparameters and how a small difference there can change how good your model performs on one dataset to another. You might find the best architecture in the search space, but if it is only as good as random guessing for your dataset, it's not that useful. The search space design and construction shouldn't be ignored because it also needs investigating. A good search space can be just as effective as a good NAS method, but there needs to be the separation of how good the NAS method is and how good the search space is. If you can have a good search space, but if you have a bad NAS method, it doesn't mean much. And if you can have a good NAS method, but if you have a bad search space, it also doesn't mean much. So I want to give an overview of some of the current challenges in NAS. So as we talked about, speed is a big challenge. There's been good strides in that. ENAS takes a day, newer algorithms can take less than a day, but speed is still at the forefront of current challenges. Search space, as we just touched on there, data agnostic NAS. As I mentioned, a lot of NAS is trained on cipher 10 and ImageNet. The hyperparameters used, the reduced computation of NAS, how explainable is NAS, and the meeting requirements. So we're going to go over these each individually. So as I mentioned, speed has been the forefront of the problem since the original paper by Zoffenly. Tremendous time saves have occurred, taking NAS from a 60+ year endeavor to less than a day's GPU time. There are some who say that NAS needs to be even faster to be able to be done in a matter of seconds. While it's a trade-off, maintaining a level of performance is necessary. So there are a few NAS methods that use performance predictors to effectively be very quick, but you do lose some level of performance in those cases. Some methods are still quite performant, but it is a problem which is generally speeding up how fast our NAS approaches are means that we spend less time doing proper evaluation, so we don't fully know how accurate these methods are. Benchmarks such as NAS Bench 201 or NAS Bench do help with this, as you can evaluate the architectures pretty much instantaneously because they're all been fully trained. However, this has other problems which we'll explain in just a minute. So the search space. So as I mentioned, a carefully curated search space can have a bigger effect than the search methods. As you et al. Found, a restricted search space that has good architectures, or that only has good architectures, gave good results to ENAS, DARTs, and NAO, while they weren't necessarily doing a good job of searching through their search space. So many NAS algorithms currently test on the NAS Bench 201 search space because it's directly comparable and it's a uniform search space and it removes the final evaluation time as all the networks are fully trained. Search space creation tools should be worked alongside NAS. Creating search spaces for novel problems is beneficial. If we have the search space used by NAS Bench, which was fully trained for Cypher10 and ImageNet, it's not necessarily going to be good for, I don't know, one of our competition data sets, which we'll talk about when we get to the competition section later in the workshop. Having a tool which, when given a data set, can grow or remove operations from a data set, from your search space, so you can have an evolving search space, would be a beneficial tool, as it can have just as good performance as a good algorithm. There's also a question of infinite search spaces. So there's work done by an ex-member of our team with his work SpiderNet, and in SpiderNet, the model or the architecture grows. It's not a predefined shape or size like a lot of other works are. It starts with only a few nodes and a few connections and adds nodes and prunes them away to figure out what's good. And so effectively it has an infinite space. So back when I was mentioning about the speed of how it is sorry, not speed, when I was talking about the search spaces and how they're not good on every data set, most NAS methods are tested on the standard benchmark data sets like Cypher10 and ImageNet. NAS Bench search space has all these architectures fully trained on both of them. So are NAS methods good at finding architectures, or are they good at finding architectures that perform well on these data sets? So because we have such a curated search space, we're now incentivized to get NAS methods that do well on specifically this search space. So if you're doing inventing a NAS method and it hasn't got good accuracy, you're probably less likely to be enthusiastic about publishing those results as you are as tinkering with it, trying to figure out how to improve your accuracy so that when you can publish, you can say, oh, we are state-of-the-art comparable. However, this search space, as I said, is constrained to only 15,625 architectures, which, well, is big in the sense of how long it would take to train each of them, isn't that big in the grand scheme of things, where we have an infinite amount of data sets that can be used and each of them have different problems. By focusing our efforts on data sets that everyone uses, we are kind of limiting the focus of where NAS can go and possibly unconsciously limiting what data sets NAS is good on. So this question is actually a big motivation for the competition that we've ran, which is the Unseen NAS Challenge. So in our challenge, the competitors had no idea what the final algorithms they would be, the final data sets they would be tested on would be. And so they had to develop NAS which would adapt and be able to handle new data sets. So hyperparameters are another problem. So as we mentioned earlier, many NAS methods tune hyperparameters after they found the final network. So they usually hold off during training the search phase and use a preset set of hyperparameters, and every architecture that they search through, if they are doing some sort of estimation or they're doing a small training window to find out how to get a validation score to rank them, uses a single set of hyperparameters. Now, as we also mentioned, changing the hyperparameters can drastically change how a network performs. And so, does it actually make sense to tune the hyperparameters after you found the model? It actually would be better to combine the process to tune your hyperparameters while you're searching for a network. Now, the obvious problem with this is including hyperparameter tuning in the search process would drastically increase the time taken. If you're searching for 15,625 networks, if you're then going to, I don't know, for example, change the starting learning rate from 0.1 to 0.01, you just doubled how many you're searching through. And every single change you do doubles the space. Another challenge in NAS is reducing the computation required. So there's a push in some areas of NAS to get it to run on mobile devices, as most people have access to these. Not everyone has access to 800 GPUs, for example, or even a singular GPU that is NAS performant or cloud time. So the original goal of NAS, as stated by Zoff in his original paper, was to remove expert time and knowledge from model creation and essentially make it more accessible, allowing someone without this expert knowledge to create models to solve their problems. Being able to perform NAS on a mobile device would remove another barrier for creating deep learning models. However, there is the trade-off as mobile devices are less performant. You would probably end up with NAS models which are low intensity for mobile devices, but aren't going to be as performant as NAS methods trained on bigger GPUs or even racks of GPUs. So explainability is another big issue, and this is a problem in ML as a whole. I have a colleague at back in Newcastle University who is researching machine learning with medicine, and he's run into this problem during his work. And in NAS, it might even be a bigger problem. So often it's not enough to have a good model. Sometimes it is important to know why it's doing it. You can have, so in medicine, for example, your model could predict whether a patient has a certain ailment with 99% accuracy. But often it's more important to know why it's predicting that. So if your model is identifying something in the image that can be used by humans, if we understood it to predict it, we can then do more research into it. A lot of machine learning is a little black box that you don't really look inside, but looking inside can often give us more answers and more areas to look into. So, for example, if we can figure out why it's detecting a certain person having an ailment, then that might be something we can look into, which might then lead to treatment for it. Another big issue, especially with the original NAS, is meeting requirements. So every problem has different requirements. For NAS to manually replace design networks, it needs to be adaptable to the different requirements of the user. And so this means what metrics optimize. As we said, medicine often might want recall or precision, because accuracy might not be as important as making sure you don't have any false positives or any false negatives. And there's hardware requirements. Do you have a phone that you run on? Do you have a GPU? Do you have a server of GPUs? How old is your GPU? What type of data is it? A lot of NAS, especially more modern NAS that I've seen, focus on image classification, like Cipher10 and ImageNet. That's not the only type of data. The original NAS methods did also include RNNs, but it seems that a lot of works have separated, so you now have RNN versions of NAS and CNN versions of NAS, and any other limitations that you might have. So we're going to talk about each of these requirements individually. So as I touched on briefly, should accuracy be the be-all and end-all? So it's not the most important metric. As I said, in medical research, you might want to optimize for precision and recall. Being able to not have any false positives can be much more important than having a 99% accuracy, but having a quite high false positivity rate. Time's another good metric. As we said, as we shown with the original NAS, that took around 60 years. If you only had a single GPU, or even 28 days can be a bit too long if you don't have that time. If your boss, for example, in industry said, "Oh, we need a network that does this now," you don't have all the time in the world. The original NAS methods focus on accuracy, but that, as I said, it's not necessarily the most important metric for everyone. So in some more recent works, we pushed towards returning a portfolio of models across a Pareto front. So NAT or neural architecture transfer is a good example of this. This is good because you may have several tasks to perform on the data. Instead of having to run the NAS method multiple times, waiting days, if the NAS method is designed to return a portfolio by the trade-offs, it will look around the Pareto front and return you a variety of methods which have different trade-offs and values. And you can use the ones which best suit your case at the time. So the hardware available can severely limit what you can do. The age of your graphic card limits what versions of CUDA are available, and therefore some NAS methods. I don't know if any of you have looked on the GitHub repository for the original ENAS method. I have. If your GPU is of a certain or is young enough, it doesn't support old enough CUDA versions to run the ENAS code as it was. And similarly, if you have a card which is too old, you can't use newer CUDA versions for models that are now being developed. I mean, the older graphics cards are also just slower than newer cards as well, which affects how long the training time was. NVIDIA and Google with their TPU were constantly in trying to improve to make the cards faster, which means that if we compare models based on how long they say they take to run now, it's not a direct comparison against the old ones, because if you rewrote the old ones on newer cards, they would have a performance increase. But your requirements based on the methods available might mean that you need to use a newer one for the time available. And if you're deploying models on machines with low-speed CPUs, you may want models that have low parameter counts. If you have a model that has millions upon millions of parameters, it might work fine on a computer, but on a machine which has got limited performance, you might need a model that has low parameters in order to get your results. So a brief touch on types of data. So as I said, many NAS methods, especially the ones that I've talked about, primarily focus on image classification tasks. Real-world data takes many forms. You have time series data, graphs, tabular data, text data, and classification is not the only ML task. Text prediction is very relevant with the predominance of ChatGPT. We have a lot of ML tasks which, at the moment, not every NAS method caters for. So there are NAS methods for each of these separate tasks, but this requires knowledge of the NAS methods. You need to go out and find which methods are appropriate for your task. There's no unified method to go and say, oh, I can run this to get a good RNN network, I can run this to get a good time series network. What about when you don't have labeled data? If you're going out and collecting data for a problem that your business has or your company has, you don't always have time to label it. So the NAS methods are often tested on Cypher10 and ImageNet, which are fully labeled, and they generally expect these labeled data sets. They expect a train X file and a train Y file. But labeling data, as said, can be time intensive and can sometimes be a more costly part of the NAS process, especially as NAS methods get quicker and quicker. If you have millions of images to label, that can take you longer than a NAS method would. So there are NAS methods such as BOSNAS that are designed for unlabeled data, but it's a similar story as I mentioned with the hardware requirements. There isn't a sort of unified approach. So you can't I can't just, for example, go to ENAS and say, I don't have labeled data. I need labeled data for ENAS. And you need to go and research which NAS methods are, which would cater to your needs. So that's about everything I want to talk about for the introduction. So just as a quick recap, we talked about what a neural network was, how to optimize a neural network, finding the best network. Then we introduced neural architecture search and how it finds the optimal network. We talked about a few methods of NAS, such as weight sharing and performance prediction, some of the issues that we've had in these NAS methods, solutions to these issues, and the current challenges.
Brilliant, thank you very much. Does anybody have any questions on this sort of stuff? Like that? Or is everybody in access? You have three components. You have the data set, you have the search space of all the architecture. In your overview, is there any training data set by selecting subset, and that will reduce your computational cost because now every single iteration is done only on a subset of data, and then delay that subset of data.
So that would probably fall under the your data policy and what you do for data augmentation. Now, I think in previous competition years, we have actually seen that, which is for the search process, they would shrink the data sets that we had in order to more quickly try and find good methods. So this is possible, but in general, I think that is probably going to have a detrimental effect. If you've got a smaller data size, it's more likely to become overfitted to it. And so any network that you get probably wouldn't be the optimum. But if you have a good enough search space, it would probably still give good results.
Mechanistic understanding of AI graphs to build as opposed to looking over the whole search space and say, okay, I'm detecting wheels, this part of the graph itself is detecting 90-degree curve. Can I now put together 4 of those because my optimal architecture is definitely looking for a wheel? I'm trying to classify the
So I'm not too familiar with that, but what you're talking about does sound very doable. It also sounds familiar to something that's NAS adjacent, which is ensembles, where you basically, for ensemble methods, you get multiple different architecture, multiple different neural networks. You get them to each individually classify the image, and then you do, and depending on what type of ensemble you use, they might take the average or the most common result, or they might have certain weighting towards one, or you could have it one that's designed to separately select, oh, we're going to have a look at this class, we're going to have a look at this class, and we're going to say what we think. As I said, it's not something that I've particularly come across a lot in NAS, but it is definitely something that I believe is possible and very similar to other works.
The one thing to say about NAS is it's quite a new area, even for deep learning. And as such, there's probably 1,001 different approaches, but people just haven't got around to trying that. So, yeah, somebody could have a go at that and go, oh, that works really well, and you get early results. Or, maybe you might try it and go, oh, actually, that didn't work, but nobody knows yet.
So you say a lot about doing NAS for architecture-specific optimization, for performance optimization, like reducing memory consumption or decreasing latency or increasing frames per second. And I wanted to know, so you talked a lot about having a search space definition, but isn't the search space something that would be very dependent on the target hardware architecture that you're searching for?
Yeah, so that, I think I did try to slightly touch on that. A very well constructed search space can have a very good effect on your final model's performance. What I've seen from when I've read the literature is originally you had NAS's search space, then you had Dart's search space, then you had ENAS's search space, and ENAS actually had two search spaces. They had macro and micro. But then when you et al. Had their paper, which was these methods are doing two things at once. They're coming up with a search space and then they're coming up with the architecture. And it's not they're coming up with the algorithm, and the algorithm isn't necessarily the important part of the process. We kind of swapped to using NAS bench as sort of a universal search space to compare against. Now, this is a problem. I think search spaces are very important, and I think we need to do more research into that and have, as I mentioned, I think we need to have a method of search space automatic construction that is adjacent to NAS. Because if you can get rid of the bad architectures for a problem, then you're reducing the likelihood of your NAS method, which isn't going to be 100% accurate, but you're reducing its chance of predicting those bad architectures. But at the same time, we do need to take into account that the NAS methods have to actually be good at finding the architectures. So for that sense, at least for ablation studies, we definitely need these curated search spaces that have the bad architectures.
But I was wondering whether there was even any work on trying to actually classify such spaces or figuring out specific search spaces according to architecture, like for instance, if you're doing for general purpose code or for GPU, or multi-GPU, you're going to have very different things to search for in terms of what's optimal for your architecture.
Yeah.
Any work on this?
It's a really interesting idea. I've not seen anything myself in that direction.
Neither have I. As I said, I think because of where et al.'s paper, where it was like it's not necessarily good evaluation. NAS has mostly focused on a comparable benchmark.
Yeah.
It is definitely something that I'm interested in looking into. I did mention that we have an ex-colleague of ours. His work SpiderNet, his search space grows. So off the top of my head, he had basically he had defined his network to be made of 3 unique cells, and in each cell, what it would do is it would start with an input node and the output node, and then it would add a third node, which would be like an L-shaped connection. And he used differentiable pruners to get rid of connections which were bad. So eventually, over his epochs, his search space effectively is infinite, but it's still limited. It didn't have infinite number of operations. So I don't think there is, at least, especially not one that's tied into, especially one that's not tied into the actual search algorithm. I don't think there is much work on that at the moment, but I could be wrong.
So, I mean, just to sort of put another rounding on this, so we started doing the work on unseen data competition because we kind of realized that everybody in the NAS community were kind of focusing in on a very small number of data sets and whether or not they were representative of what people really wanted to do, because you wouldn't really in anger run a NAS approach on CVPR or ImageNet because we already know what the better networks are for those, because well, we've got NAS benchmark to start with. But likewise, I totally agree with you that the whole search space, again, we've kind of focused in on these NAS bench search spaces, which may not be good for certain types of hardware, may not be so good for certain data types. Yeah. Yeah.
Always towards being better at executing our general purpose
Yeah.
code.
Yeah.
But if you try to run it on a GPU or a mobile GPU, can actually be better.
Yeah.
And when I look at some of the structures that are suggested by NAS, like the data center,
Yeah.
like all trying to reduce the number of operations. But for a very parallel architecture, actually your best latency doesn't.
Yeah.
I mean,
I have the impression there's a lot less work being done.
I agree.
My question is kind of to check with you that
Yeah,
this is the case,
yeah.
if I'm not missing anything.
Yeah,
no.
I'm looking at it.
I would agree with you, especially because in the mobile space, you want to have as few multiply, accumulate operations as possible, rather than their less parameters. So certain algorithms such as NAT, for example, new architecture transfer, which, as I said, it returns a Pareto front. I can't remember if it does it inherently, but you could add the number of multiply accumulate operations to its trade-off value, which would help with that. But it's, as I said, it's not every it's definitely not every method.
Or you could do something as coming up with some formless predictor that you have for the performance of the cost. But yeah, the lot that I think could do there, but I invested in.
Yeah. So I think it'd be really interesting to try and do a competition based around that, to sort of try and push people away. Fixed architectures, but I can't quite figure out. So you've got any ideas? I'm quite yeah. Any other questions? Yeah.
So what was that? Sorry, I couldn't hear.
Sorry.
There's a microphone. There's a microphone there if you want to speak.
Yeah, sorry.
Yeah.
I want to ask that that's right. So, when I review these, I say that their contributions are focused. Maybe some papers are focusing on designing lower and large cells, the time when they are using local. And I wonder that it can be a kind of huge contribution, because when we starting NAS, we don't want to design large molecules. Instead, we are designing these small cells, and it's getting larger, and it takes more effort to design these cells. So I wonder that is it the correct direction, or maybe we turn to simpler cells, or maybe not designing the cells manually. So yeah, that's my question.
Okay, so if I get, so you're asking, should we return to searching for a whole network rather than cells? So that's a good question. It's, as I mentioned earlier, the reason that we switched to cells is because we found for a lot of like the manually designed networks such as Inception and ResNet, they naturally, or I guess not naturally because they were designed, but they started having these repeated blocks. And so the researchers that noticed this were like, well, if these networks that are performing very well have these blocks naturally occurring, then we should look into that. And it has a very good time save. It's a lot harder for example, with performance predictors where you encode a network into some sort of like tokenized numerical value, representation. It's a lot harder to do that on a bigger search space, which isn't a cell. Now, I do agree that searching on a full network rather than a cell is probably, you're probably more likely to find the optimum than just by using cells. Even with Inception, as when I showed earlier, it wasn't just blocks, they had like offshoots. It is an interesting, I think it is an interesting thing to look at, especially now that we've got faster graphics cards and faster techniques. I would like to see more NAS looking towards revisiting the older macro search space, as NAS called it. But at the moment, I still think that micro is probably going to be what we use for a lot of it, just due to how fast it is compared.
Question is agnostic data set. Do you specify some general parameters of the data set, like the size or image resolution, and so on? Otherwise, I don't know how the architecture can be optimized, not to overfit. We don't even know the scope of the data set.
So in the competition, we did for the data agnostic. We did not specify it because, so if you limit your NAS method to color images at 32 by 32, theoretically, there might be some NAS method which is really good at figuring that, but not all data can be encoded as that. So for some of the data sets that we use, for example, one of them is, I think it's 64 by or 32 by 128. And that like to use the full data. And so you can't just use the 32 by 32 because you're missing a lot of data. There probably is it would depend on how you train your method, because for data because for the data agnostic, the problem we have isn't that we think that like the methods themselves are particularly optimized for Cipher-10 ImageNet. We just think that due to probably some unconscious biases and the search bases, they're going to be more pushed towards being better at those data sets. To an extent, I actually think that looking at the data agnostic without specifying, so that you need to make methods which take into account different shapes and different number of channels and different sizes, is actually going to lead towards less overfitting, because you can't put anything in that is specific to that. You can't plan your layers to be like exact reductions of a certain size or for a certain number of parameters.
So you could come up with a really deep neural network, but have a very small data set, and it should still work.
So the small data set, yeah, that is a problem, but in the real world, you might have a very small data set, and you need to, if you want a generalized NAS, you need to be able to consider small data sets, big data sets, simple data sets, complex data sets. It is probably an ever-shifting goalpost, and it's probably less so a thing that is possible and more of a selection of trade-offs where you'd have to build a Pareto front. But at the moment, most NAS methods are focused on relatively simple, very specific image classification sets, where if we made it more data agnostic, we'd have more options and it would be more available to other problems. For example, if I went and got a data set of, I don't know, buildings around Vancouver and try to identify what street they're on, I'm not certain whether NAS would perform as well on that as it does in Cipher-10 as ImageNet, because all the evaluation has been done on those two data sets.
Brilliant. Time for one very last quick question, if anybody's got it. Yes.
Yeah, I have a general question about the goal of NAS. So it seems that most people are really in the NAS community focus on like searching for single fast neural architectures. I wonder, do we want to care about like searching for a set of equally good architectures? Because I would imagine the optimization landscape of the NAS problem would have multiple mode. So it sometimes it seems to be better that we have a set of good architectures, or even a probabilistic distribution of the good architecture, where we can like adapt, be more adaptive on different data sets.
So yeah, definitely, I think. So as I said, so there is some works such as neural architecture transfer, which do return this portfolio of multiple different models that you've optimized between a certain number of parameters. And I think that is the direction to go. As I mentioned, that it isn't accurate, actually isn't a problem. Now, the thing is, a lot of methods are directly comparing on that. So when you see a paper, for example, BOSNAS, for example, they'll report our method got this percentage on this benchmark showing state-of-the-art performance. And this is kind of the problem that we're saying, we've been saying, which is like these search spaces and these data sets are kind of pushing towards a certain area which isn't necessarily with the original intention of NAS. As I said, Zoffenly originally wanted to remove expert knowledge and to reduce the time it takes to make these networks, which in effect would make it more accessible to everyone. And for a lot of NAS, it doesn't necessarily do that. In last year's conference, we published a short paper about the and difficulties of reproducing it, or reproducing a lot of math methods. And we found that, especially ENAS, as I mentioned, I looked at the GitHub. It's not, if you were a non-expert, finding which NAS method is good for you and then getting it running can be a challenging task. And so this kind of towards that end. Because as you're saying, if I was a doctor, and as I was saying, using my medicine example, I wanted an architecture that has low precision, I would have to, if I found a method which I think would work with my data, I would still, for most of them, have to go in to the code itself, manually change it to optimize for precision or recall, which should be doable, but that's speaking from someone who knows how to look at code and knows how to use GitHub properly. So yeah, I think NAS should probably, move towards being more of an application that you can download and give a data set and then get results out of to reduce the amount of knowledge required.
Brilliant. I think it's time for the coffee break now. So thank you very much, folks. 10:40 we will restart at. Just as a reminder, there is a form going around if you could sign up. As I say, we need evidence to prove to the people who pay for us to come here that it's worth us coming here. So if you mind signing up to that. We've got a mailing list where we're going to advertise about future competitions and future workshops. And there's an online form there, which is exactly the same as the sheet of paper that's coming round. So you can either fill in the sheet of paper or you fill in the online form. It's up to you guys. But we'll see you in around about half an hour.
But just quickly, if either Andrew or Dongling Ma, the two of our paper submissions, if you're online, can you send a message to either me or Steve on Zoom? And if you're in the room here, can you come up just so we can organize what we're doing? Thank you.
Brilliant. Okay, brilliant. Thank you very much, people. I hope you had a good break. Did you find some coffee? Because I didn't. Was it hidden downstairs or something? I don't know. Anyway, welcome back after the coffee break. We're now going to start off with our first of our 8 papers. So I'm going to move on to the paper by Andrew. Now, Andrew, unfortunately, was unable to actually physically get here for this workshop. So he's actually sent us a nice video. He is online, so he will be able to answer questions at the end of his presentation. But let's try and play his video and see if everything works.
Hello, my name is Andrew Kowalski. I come from one of the company called Behind, and welcome to my presentation on paper. Systematic architectural design of scale transformed attention condenser DNNs via multi-scale class or representational response similarity analysis. I would like to thank my co-author and supervisor, Professor Alexander. So the title of the paper is but at a high level, what I propose in the paper is a type of analysis that helps reveal certain characteristics of data representation of data as it travels through a neural network, and which I use observations from this analysis to propose modifications to existing neural network architectures. So here's a TLDR of the methods proposed throughout this paper. Starting with a neural network, at each layer, I capture the latent representation of data as it moves from the beginning of the network all the way to the end. And then using the latent representation of this data set, I calculate this neighbor graph of all these samples. And I repeat this at different scales of the data. So starting with normal resolution, I'll downsample by half and then by quarter, and keep going. And then using neighbor graphs, I will look at the class-wise similarity between any given sample and all of its neighbors. And then using this information, I can aggregate it and then plot these similarity curves of your data as the representation changes throughout a neural network at different scales. And it is this entire process of what I call multi-scale class representational response similarity analysis, or class REPSIM for short. The goal of this form of analysis is to add to the arsenal that we use to build deep neural networks and to better understand how your data changes throughout a neural network, and so we can make more targeted decisions in design. By applying class REPSIM to different combinations of resonant cell architectures and data sets, I observed unique patterns throughout the network at different scales of your data set that allowed me to propose a new form of network architecture, which I called scale transformed attention condenser modules. The architecture itself follows the same overall principle of attention condenser module, which is built around compressing the data, performing operations on it, and expanding it back up, and then using that new information map as a self-attention module, much like the standard squeeze and excitation based modules. When stack modules are integrated into resonant cell architectures, we demonstrate that the model achieves better performance for the same number of parameters as other resonant cell architecture improvements, but with the benefit of requiring significantly less performance. And this benefit, of course, comes from using the significantly reduced feature map sizes present in the stack module. So backing up from that, let me just approaches proposing this paper relate to things previously proposed. So the study of representation has been, of course, studied for some time. Methods like CVPR directly compare features between layers of a neural network, allowing one to see how the representation between different blocks in and around network change as it progresses. So, this sort of analysis is interesting because it allows you to show which layers in the neural network are actually learning within this information. These approaches are linear code, where each layer you learn an auxiliary linear classifier, which determines how linearly separable species are on that specific layer in the network. And now, construct C, which we propose in this paper, is somewhere between speaking and graph is centralized rather than a constant similarity score of the construct C. And we have embedded in the information that CTA when it's applied to a layer. But instead of using this information directly, we use the information much closer to linear coding, just more complex version of separability. Approaches like intrinsic functionality approach calculates the dimensionality of your latent representation. This can be used to help determine if there have too many channels. So all these approaches what's happening in the ultimate goal of being able to design and build. Using these approaches and other space approaches, there are methods used in different architecture. It's auto-ticket, generative synthesis, there's never laws, all attempt to affect directly or indirectly the structure of the neural or the late representation that it takes as it moves. Of course, all these approaches come with trade-offs that it helping improve the performance of your network and also come with computational complexity. Of course, sometimes there are contributions that add both performance and help you reduce the complexity, much like the skip connection did. Allowed say BGD style network to be deeper, but also made it easier for the network to learn. Which then allowed less weights and blocks to be used to achieve similar. Using site-based networks with based models by having second parallel track that will reduce feature maps to dense vectors, then be used as a channel excitation map. The stack model proposed in this paper can be seen as an original version of this submodule, but whose design is motivated by the insights we gain from our construct sim analysis. So now let's take a closer look at construct sim analysis. So here's a sim again, which shows the three steps one takes one construct sim. First, the latent representation at every stage in the neural is calculated for every sample in a given data set. And then a K-linear schema graph is calculated for each of the sets at each of the layers. This process is repeated for every single scale of the data given neural. Of course, the scales of compute are dictated by what spatial resolution the feature maps are. To be clear, the cooling happens at the feature level, not at the input level, such that features are scaled and not the input data. Finally, using graphs, we can calculate the average class similarity in every single sample within the KNN. And then for a given scale, we can plot how the class similarity changes from layer to layer within a neural network. Then by different scales, we can see how the class similarity changes. And here's some actual results of what it looks like when you apply class referencing to a ResNet 20 model and two different data sets. Is what it looks like. We trained our ResNet 20 model trained on CVPR 10. And on the right is what it looks, what class looks like when a ResNet 20 model is trained on NAS 64 by 64, which is just a cool version of the one. It still contains all the samples and all of the thousands. For each of these examples, we applied class referencing 5 different scales. 4 of the scales were consistently applied for every network, but for the global average cooling scale, we applied the maximum cooling possible for any feature. The x-axis for each plot shows the layer index in the network, and then the y-axis shows the measured class similarity for that layer. Looking at the CVPR 10 example, when node scan is 5, so from the starting at the beginning, we see that there's a small decrease in class similarity. Around layer 4, the curve starts to change. Before it increases back to close to where it started. And then starting at layer 8, we see a dramatic decline in the class similarity as we approach the outclass. So one of the initial interesting trends here is what happens between layer 0 and layer 4, where the class similarity actually decreases with the first stage of this. Observation as the initial classification. One of the interesting things about this phenomenon is that it coincides with the same early years in which the potentiality of the network is spike. Meaning that the network starts to use higher intrinsic connection for its link representation to represent data. And then the second phenomenon is the spike that begins which also happens to coincide with the change of resonance stage. Moving up to higher scales of the network, we see that the general trend of the class similarities progresses, but the general trend of increasing. When we move to a 2-times scale reduction, the most major change is in the middle area. But then after that, the progressive scale changes, the change. One more interesting phenomenon is that the transition between layer 4 is the first time where the observed class similarity score actually sees a decrease in the middle. So overall, there seems to be a key spatial resolution at which class similarity is most prominent. And it is this key observation which motivated the design of the stack module. And now, just quickly looking at the right, only an overall general decrease in class similarity, which is just the result of larger number of classes. We see many of the same trends, including the initial decrease in class similarity in initial layers and a spike in class similarity. One of the key takeaways of class represent is that there are key spatial resolutions at which the class similarity between classes is highest for any given point in the network. And the reason we hear about class similarity for classification networks is that it's ultimately the name of the game. So what we propose in this paper is a specific design of an attention condenser module to explicitly exploit these key spatial resolutions of your feature maps within a neural network. The design of the stack module follows the standard trend of an attention connection module. And it's very similar to squeeze and excite module, in which the spatial features are pooled, but unlike it's in squeeze and excite, we do not do a global average pooling. We only scale by a specific feature resolution. And then many standard convolutional neural network operations are performed. Convolutions, relative convolution in the same way. And then finally, we upsample again by the same spatial resolution we initially pooled by. And then finally, using upsample attention map, we multiply it with the input, effectively another skip connection. But this time, it's mainly used to draw attention to specific regions with. So very quickly, here's just what a squeeze and excite network looks like. As you can see, it's very similar to the stack module, as it follows many of the same design principles. And then here is another different extension of a squeeze and excite network called the bottleneck attention module, or BAM module, which attempts to achieve very similar results, but with a more complex design that has both a spatial parallel track and full track. And so to compare these approaches, we integrate them into a neural network, a resonant neural network, at every single neural network block in two different placement configurations. Here are the two different configurations. On the left, there's a standard configuration, which places the residual block operations, followed by the stack module or one of the other two modules, and then followed by the normal residual skip connection. And then on the right, there's the post configuration, in which first you have the normal residual block with the residual connection, and then the stack module or one of the other two modules inserted after. And this terminology is from the original squeeze and excitation. And then in addition to the other network architectures, we'd also compare to upsized resonant 20 modules that were either twice as deep or root 2 as wide, such that either the number of parameters or the number of flops are approximately equivalent to the network comparisons. And here are the results of our comparison on our resonant 24 model, 64 by 64, where the center of the circle is the performance of the model, and the area of the circle is proportional to the number of parameters of the network. And then for these tests, we use a pooling window size of 8x. And also the performance of each of these models is the result of 8 independent points. So overall, the stack module, for a small increase in flops, results in a very significant performance increase over the base resonant 34 model and also the SDNet. And also, while the stack module does nearly double the number of parameters in the network, there's a lot more computation efficient with the parameters it has compared to both the other two resonant 34 variants, the 2XD and the root 2Y, but also compared to the BAM module. And now, here just very briefly are the actual quantitative numbers for both the chart I just showed you and additional experiments we ran. And for most of these other configurations, the stack module outperformed other modules it was compared to, with often the closest competitor being the root 2Y resonant models. But again, while we're requiring slightly more parameters than the root 2 resonant stack module are significantly less ones. And also the best placement configuration for the stack module was in the standard placement. In addition to the comparison of different model architecture types, we also did collation tests within for the stack module itself. All our tests were performed on ResNet 20 network, trained on 2 different data sets, CVPR 10 data set and subset of an internet 64 by 64 days. We explored many different hyperparameters of the stack module, including the size of kernel used in the network, the location of the stack module within the network, also different cooling sizes used in a network, and various hyperparameterization selection strategies for determining which parameters to use. Overall, our application tests demonstrated that the stack module is pretty robust in terms of hyperparameterization selection. For more information, you can find it in section 6 of our paper. For future work, we plan on investigating comparing class representative to other analytical mentions, like the ones mentioned earlier on in this paper. We plan on using class representative on larger model and data set pairings. And also, we plan on investigating what integrating a stack modules into other DNN structures would look like. Thank you.
Thank you very much. So Andrew is at the other end of a Zoom link. So if anybody has any questions, can you let us know? So Andrew, just to check, are you there? Maybe not. Oh, excellent.
Hello?
Oh, yeah.
Hi. Sorry about that permissions issue.
You should be able to just drag that across. Which way is your? Right, it's this one. That's says Andrew. Anybody got any specific questions? So Andrew, I was quite interested in the applicability of this technique because it seems to work quite nicely with the 2 data sets you trained it on. Have you looked yet at other data sets? I know you talked in the future work about moving into other data sets, but have you tried anything else yet?
Yeah, mostly on the standard toy data sets, MNIST. I tried on ImageNet, but there's of course, calculating the KNN, it can be very computationally expensive. So its applicability to say like normal sized data sets, there's still a few hurdles to overcome. Of course, standard approaches like that other methods use is just to do directly downsampling before calculating the KNN graph. But we have observed in what data sets I have tried, you see a lot of the similar trends. I'd say one of the areas that might, you see these nice curves when you apply like the vanilla ResNet model, but once you say apply the class representative method to a ResNet model that has the stack module inserted, a lot of the trends change ever so slightly. You don't necessarily get the nice separate patterns across different scales. The model seems to figure out how to best use most of the scales you can provide it with.
Brilliant. Any final questions? I think in terms of time, we're probably going to need to move on. So let's just thank Andrew once more.
Thank you.
And I think we have the actual person here. Oops. Yeah. For presentation 2, which is Don Jing. who is actually in the room. Excellent.
Where is the mouse?
Have the PDF.
Yeah.
Yeah.
Just opening it now.
Just whilst he's setting up there, could I just ask if anyone has not signed up?
Full screen. Over here. And then how do you full screen?
Control something people are attending.
See. Okay, so if you just use the arrow keys, it should work.
Let me set up my timer so that it won't overrun.
So handing it over.
But I cannot see I cannot see the PDF there.
A few technical difficulties.
Great, thank you. So hello everyone, I'm Dong Ma from Villanova University, United States, and today I will be presenting our paper on the topic of efficient vision transformer architecture performance ranking using hyperdimensional computing. So here's our table of contents today. We'll briefly introduce the motivation behind the work and some preliminaries background about hyperdimensional computing, and then we're proceeding to the PerfHD, which is the framework we propose with some evaluation and results, and finally some final words for discussion and conclusion. So the first part of the motivation actually come from the neural architecture search, NAS, and as also already introduced in the tutorial, the NAS process is not a trivial effort, right? And there are some existing methodologies such as SuperNAS, weight sharing, one-zero-shot learning, etc., to enhance the efficiency of the NAS process. But there is still one key question to ask. So is there a way to predict or estimate the model performance just based on their parameters or hyperparameters instead of actually training or testing them? So this is the major motivation of this work, which attempts to propose a new potential research topic for extremely lightweight and efficient, or particularly data efficient architecture ranking of different vision transformer models. And the approach we use here is the hyperdimensional computing. So the hyperdimensional computing, or HDC, is an efficient brain-inspired computational paradigm that processes information in the high dimensional space. So I have a delicious example about how to use HDC to classify between two kinds of fruits I like, the durian and jackfruit. They are both very delicious, but hard to tell them visually. So suppose if you want to develop an HDC model to do this task, what it will do still follows the general machine learning flow. First, you will have an feature extractor, which converts the realistic input such as images into some latent variables, and the classifier, which leverage those latent variables to make classification. In HDC, the feature extraction process is the so-called encoding here, which encoded the input realistic images into a high dimensional numerical vector representing it. For example, you have the durian image here and use some sort of encoding algorithm, it will be converted into a numerical vector representing the durian. When you do the classification in HDC, it uses the similarity check. I think it's similar to the clustering. In the third row, we have an image with unknown class, and we want to know what kind of fruit it is. So we use the same encoding scheme to encode this image into another numerical vector, or the latent variable, and check the similarity between this vector with the vectors representing jackfruits or with the vectors representing the durian, and pick the one with higher similarity as the predicted label. So HDC has some advantages. The model itself is very compact, and the training and inference of HDC is energy efficient. The implementation is also straightforward. But HDC also have the major disadvantage that it is relatively a weak classifier or learner. So it cannot really work on larger data sets such as ImageNet or even in CVPR. So the application using HDC nowadays mostly focus on small scale of data such as the edge intelligence or embedded systems. So with those motivation, we can now go into the background about hyperdimensional computing. So the fundamental elements of an HDC model is the hypervector. The hypervectors are used to represent the information in the high dimensional space. There are three key properties of hypervectors. The first is the high dimensionality, which means that the amount of numbers in the numerical vector is in an extremely high number, usually larger than 10K. So normally, when you do the latent embedding or something like that, in general machine learning algorithm, your objective is to reduce the space, right? To reduce the number of numbers in the latent vector. But the hyperdimensional computing actually goes on the opposite way. The second property of hypervector is holographic, which means that individual numbers inside the hypervector does not carry unique meaning. Also, two randomly generated hypervectors are approximately orthogonal to each other due to the high dimensionality. Because hypervectors are numerical vectors, so it supports some operations, including the scalar operations of element-wise addition and element-wise multiplication, as well as a permutation, which is the cyclic shift of the numbers inside the vector. So another key concept in HDC is the memory. The memories are the specialized clusters of hypervectors with different objectives during a learning task. So it can be roughly considered as the parameters of the model. There are two kinds of memories in HDC, the item memory, which is the non-trainable part of the model. They are usually randomly generated, which is used during the encoding process to help with encoding the realistic images into embeddings or hypervectors. The associative memory, on the other hand, is the trainable part of the HDC model. It is used during the similarity check to make the predictions. So now we can go into the PerfHD framework we propose. So the problem formulation here is that this task or this problem actually come from the workshop last year here, which features a computation about of 3 tracks. And the second track of this computation is to rank the vision transformer model performance based on the architectural parameters. The major challenge of this computation is that the training data is extremely limited. So they provide like 100 key different architectures, but only 500 of them are actually labeled with their performance ranking. And the task is to learn on this extremely limited data to predict the rest of the architecture on their performance ranking. And the parameters of each architecture considers something like the depth of encoders, which means the number of encoders in the encoder stack, the number of attention heads, and some ratio of the MLP. And the search space is also relatively large. And another note is that we are inspired to use HDC because of the limited training data, as HDC is known to be performing better on small scale of data sets. The PerfHD has probably 3 or 4 key steps: encoding, training, retraining, and inference. The encoding process is to encode the architecture parameters to an hypervector representing it, just like encoding the durian or jackfruit images into hypervectors. So here is a typical architecture of an vision transformer. And we can see that all the 3 parameters used in the context focus on the encoder stack. And for example, for the number of heads, this parameter, the possible values of number of heads in the context has 3 values, 10, 11, and 12. And for each unique parameter, we develop an atom memory for that. For the number of heads memory, because the possible number of parameters are 3, so we have 3 hypervectors, each representing the number of heads correspondingly. For the gram-based encoding, we use 2 atom memories out of the 3 atom memories, the number of heads memory and the MLP ratio memory. So it is called gram-based encoding because we treat each encoder in the encoder stack as a gram. And within each gram, we know their number of heads, right? And we also know the MLP ratio of it. So we use these two information to get the corresponding atom hypervector in the atom memory. And we do the element-wise multiplication of these two hypervectors and then do a permutation based on their index in the encoder stack. And we finally add all the gram hypervectors together to get the final hypervector representing this architecture. In the record-based encoding, instead of use permutation, we introduce another memory, the depth memory, and do another layer of element-wise multiplication to guide the final architecture hypervector. Okay. So the next step is to train the associative memory. The training is very simple because it is just the weighted sum of the encoded hypervectors. So the principles here is that the architectures that perform better, which means that they have higher ranking, will be assigned to a heavier weight. So that when you do a weighted sum of those hypervectors, they will contribute more to the final associative memory. So in this sense, when you finish training, the associative memory actually is a collective of all the better performers of this task, right? And of course, in the dataset, it is provided, the labels are provided as ranking. So we need some sort of conversion to convert the ranking to the weights. So the next step is inference and retraining. The inference is to use the associative memory to make predictions of the architecture rankings. In PerfHD, we use cosine similarity as the similarity check for the prediction. Consider an H-way representing an architecture. We calculate their cosine similarity with the associative memory. If it has a higher similarity, it means that it has a higher potential to be considered as a better performing architecture, or vice versa. And of course, other metrics to calculate vector similarities, such as the Hamming distance or Euclidean distance, can also be applied here. So the last step is the retraining, which trying to update the weights so that the HDC model could perform more accurately on the prediction. The retraining is to update the associative memory by the difference of weights to make sure that the similarity ranking of each architecture is consistent with the ground truth ranking. So basically what it does is to make inference on all these samples in the training data. And for each architecture in the training data, you will have the similarity metrics, right? So based on those similarity metrics, you can perform the ranking of your training set. And you compare this predicted ranking of the training set with the provided ground truth training set to calculate some sort of loss and use the loss to update the weights in the model. And this updated weights will be used to retrain the associative memory, to update the memory to make more accurate predictions on the ranking. So now we can look into some evaluation and results. So a deeper look at the data set, it is provided by the second NAS challenge last year. It is on the Weimar UFO benchmark with 8 different computer vision tasks. And we also compare some baselines, which are all the participants of the competition last year, including the GPNAS, which is the baseline provided, and the GPNAS ensemble, and some boosting algorithms. All the results are from the reports of the participants of the competition. And the metrics to calculate the ranking consistency is the Kendall-Tau score. So here is a table comparing the performance of different models. We can have 2 major observations. So the first one is that the proposed PerfHD actually achieves comparable accuracy with the top performer GPNAS. We are a little bit falling behind. And within the HDC, PerfHD with record-based encoding outperforms the PerfHD with gram-based encoding. And we think that this is because the depth memory added in the record-based encoding provides additional hyperdimensional space to represent or learn more information from the data sets. But more importantly, we also compared the efficiency of the model. We can see that although the GP-NAS ensemble, which is the best performing algorithm in this work, they have great performance, but when we run them using just one GPU, the NVIDIA P100 GPU, they take relatively longer time to run. But the PerfHD with record-based encoding we proposed finish all the predictions of all the 8 tasks in just 1 minute. So we think we provide a balance or trade-off between efficiency and performance. We also do some preliminary design space exploration to investigate the impact of dimensionality of hypervectors. We show that when we increase the dimensionality from 10K to 100K, we show some marginal increase in the performance of the model. But any increase beyond 100K of the dimensionality will not always grant you a better performance. We think that in this sense, the model has saturated and you have enough vector space to represent the information. So the bottleneck of limiting the performance to growing further is not the hyperdimensional space, but maybe on the encoding algorithm. So we have some final words for discussion and conclusion. So why HDC can achieve comparable performance, but still with better, achieve better efficiency, but still with comparable performance. So the efficiency of HDC actually comes from the simplicity of processing. The training, retraining, and encoding in HDC are actually just linear operations. The cosine similarity is also a simple calculation to speed up using GPU. And the complexity of hyperdimensional computing models does not scale when you have a different number of tasks. So even if you increase the number of tasks from 8 to 100, we still use, the HDC still use the same set of atom memories for encoding. So the size of model does not significantly grow. So what are the limitations of this work? Of course, the encoding process is not application agnostic. You need manual design of your encoding process. For example, if you add different parameters into the dataset, you will redesign the encoding methods. So this solution is rather ad hoc. So it is a possibility that we are just lucky to be a better performing architecture in this context. But how about other scenarios in the NAS? And again, HDC has a relatively weaker learning capability. So we are not going to compete with the first place in the competition. So in conclusion, in this paper, we leverage the advantages of hyperdimensional computing and propose the PerfHD for vision transformer performance ranking. And this is a preliminary work, and we aim to open a new potential research topic that can improve the efficiency on the effort on the NAS. Okay, thank you, and I'm open to some questions.
Thank you very much. Any questions?
So a question I have, which is related to the show at the beginning. When you talk about being able to convert the images into latent encoding, is there a possibility within your method for it to work on non-image data, for example? How difficult would it be to apply, I don't know, a time series data set or a tabular data set or feed text to this method?
Yes, that's a good question. So it's still, I think, similar to what I talk about in the limitation of this work. You need to design specific encoding methods to tackle different data sets. So in this, maybe we have a tabular data or something, you design the gram-based or record-based encoding for it. But if you have, just like you said, the time series, we need to develop the encoding for it. And this process is completely manual. So which means that the system designer need to know about the application they are doing and design specifically. This is the major bottleneck for the HDC. As for something that has like 0 to no domain knowledge about the application, they may fail to come up with a good HDC architecture, to achieve such a comparable accuracy.
Thank you.
Oh, sorry. So just sort of looking at the idea of layers on layers. You're saying at the moment it's you build up a human has to come up with a way of encoding the HTC. Do you think it would be possible at some stage then develop a machine learning approach that could actually work out how to do that? Like a lot of these things just add another level of complexity.
So you mean it's still about the encoding process?
Yeah. So you're saying at the moment it needs to be a human who comes up with that process. Is this something a machine learning system could learn how to do?
Oh, you mean to automatically come up with the encoding scheme? I think that's a good, actually, potential topic to investigate because it's similar like doing NAS for the HTC itself, right? I think there is 1 or 2 papers talking about that, but they still focus on limited scope because the HTC specifically for like ECG classification. So there is a limited application of that. But yeah, that's an interesting topic to think about.
Brilliant. Thank you very much. Questions further? No bother. So David is now going to introduce the information about the competition.
Yeah, I'm just going to reset my setup here, so just give me a second. So yeah, so now we're going to talk about the unseen data competition, give a brief overview of it, and then we have a presentation by the winners about their method. So we're first going to talk about the motivation, and then we're going to explain how the competition itself worked, the validation data sets, and the final data sets that were used as part of the competition. And as I said, then we'll move to the winners. So as I touched on in the tutorial at the beginning of the workshop, NAS methods are traditionally designed with the standard benchmark data sets as the final evaluation. The score that they get on that is used and compared against the others. So the idea behind the competition is designed to get people to create NAS methods that will work well on data sets without knowing what the data sets that they're going to be compared on are going to be. So the hope of this is to encourage NAS methods which are more adaptable and more generalizable to data sets than more standard methods. So if we break down the competition, it was split into 3 phases. Phase 1, we had users download our CVPR starting kit and work on their NAS methods on their own machines using their own resources. Then we opened phase 2, and phase 2 was open for originally we intended for 2 weeks, but due to some issues, we had to extend it by a week. And this was, the users submitted their methods to our website, and it would run their methods on small data sets for about an hour. They needed to have a method which passed through our pipeline, basically assuring that it worked, to get through phase 3. And phase 3 was a 24-hour run on 3 separate data sets. So the competition where we scored the participants based on a scoring system that used an adjusted score that represented how well you did on all 3 data sets. So all 3 datasets were ran on ResNet 18 to generate a baseline score, which was used when calculating the user's adjusted score. So this is the formula. So the adjusted score for any dataset is the raw score, so the accuracy that the user got from the NAS method, minus the baseline, and then that is times by 10 divided by 100 minus the baseline. So this meant that it was at max a positive 10 and could be negatives, well, as negative as it could possibly go. So we clamped it so that it was at maximum 10. So if you did really bad in one data set, it could only take you down by -10. But if you did really well in the data set, it could only give you +10. But to get +10, you'd have to get 100%. And we summed together the 3 scores for the data sets, which would give you a score anywhere between -30 and +30. So yeah, as I mentioned, the 10 binds to 100 is the scaling factor. Okay, so we're first going to talk about the hidden data sets of phase 2. So we used 3 data sets of phase 2, which we called Congo, Ganges, and Rhine. And they were created by reducing the size of popular known data sets by about a factor of 10. So Congo is cipher 10 data, but instead of using 50,000 images, it only had 5,000. And Rhine was using the German traffic sign recognition benchmark dataset. The only one that was slightly different was Ganges. And so Ganges was made from text using Project Gutenberg. In fact, so the dataset which I shrank down is the Gutenberg dataset, which we developed in previous years to use for the competition. So the 6 classes of the Ganges or the Gutenberg dataset are 6 authors from the Project Gutenberg corpus. So the classes were either Thomas Aquinas, Confucius, Hawthorne, Plato, Shakespeare, Tolstoy, and it was a visual encoding of some text from each of their works. And so the method had to figure out which author had wrote what. But they were very small data sets, only a couple thousand images and only run for an hour. So the results weren't very indicative, but it was to test to make sure that it was working. The phase 3 data sets were also consisted of 3 data sets, but these were bigger, about 50,000 images each. So we have Chester, which was a data set based on games of chess, Isabella, a data set based on concert recordings, and Sadie, which is a data set based on satellite data. So Chester was a data set that a lot of people actually struggled with when they got to phase 3. A lot of solutions failed due to some of the, how Chester is encoded. So the biggest reason why this failing is that many of them assumed that the data sets would either consist of 3 channels or 1 channel. While you can see here, Chester contains 49,998 images, which has 12 channels. So Chester is based on chess dataset, and the 12 channels is a one-hot encoding of the 6 chess pieces on both sides. So channel 0 to 5 would be the white pieces, and then channel 6 to 11 would be the black pieces. And so like 0 would be a white pawn, and then 6 would be a black pawn. And the board positions were taken from Grandmaster Games of Chess, which are publicly available on several chess datasets, a few moves before they ended. And the model is to determine whether or not it was a draw, a win for white or a win for black. And our benchmark had about a score of 57.826%. The Isabella dataset was another one that some people tripped up on. It is bigger than the other datasets. So it has 50,000 images with a shape of 1 channel, but then it's 64 by 128. It's named after the Isabella Stewart Gardner Museum, who originally published these this audio data, which we've used for the dataset. The 4 classes represent the type of music. So it's either classical, romantic, baroque, or 20th century. So as I said, so Chester and Isabella, a lot of people stumbled because they expected, and they didn't necessarily expect the dataset to be have a large number of channels or be as big as Isabella was. And the benchmark result for Isabella was about 62.02%. And finally, we have Sadie. So the Sadie dataset is again 50,000 images, but this time it's in a more conventional shape of 3 channels by 64 by 64. So the Sadie dataset is made up of big Earth patches of satellite data over European countries, and it has 10 classes representing Austria, Belgium, Finland, Ireland, Kosovo, Lithuania, Luxembourg, Portugal, Serbia, and Switzerland. So we had a benchmark result there of 80.33. So we had over 20 people take part in phase 2. 15 of these were entered into phase 3. However, only 5 successful submissions were made against the 3 hidden datasets. So in third place, we had Yukan Yang from Ant Group. I believe his method was had a total score of about 2.9. So this isn't that large, as max could be up to 30, but as you'll see when I reveal the scores of the top two, it isn't as drastic as you think. Some of these data sets were just quite hard for NAS to perform on. Second place, we had Jingrong Ji from Sichuan University. I believe he was about 4.6 in score. And finally, we have Aojun Liu, again from Sichuan University, of about, I think, 5.7 total score. So Aojun Liu and Jinguang Ji appeared to have been working together, and their submission only differed by hyperparameters. So these results are provisional. And we have a joint video by both of them, which is explaining their method. And before I play that, I'm just going to double check Zoom is okay. So hopefully this will work. Okay, so I'm gonna hand it over to them.
Hello, ladies and gentlemen. I'm Jingrong Xie, a student of Sichuan University. It's my pleasure to share our NAS approach to you. We will introduce it in 3 parts, which are search space, search strategy, and performance evaluation. Firstly, we use ResNet block and max pooling to construct the search space. Then we encode these architectures as variable length keys. We use 48 or 64 to represent the basic blocks whose base number of channels is 48 or 64, and the code 1 means doubling the number of channels in blocks after it. The code 0 represents the max pooling layer. This constraint is to ensure the number of network parameters is within the suitable range. And this graph shows the correspondence between coding and architectures. You can see that the code 1 doubles the number of channels. Subsequently, we use regularized evolutionary algorithm to search architectures. Specifically, we randomly generated a number of architectures and evaluated them to construct initial population. In initial population, the network depth of architectures is unimportant as our algorithm could find suitable network depths automatically. In population update iteration, tournament selection is used to select a parent architecture. Then a mutation operation will be used on the parent architecture to generate a child. After the child architecture constructed, it will be evaluated and added to the population. Meanwhile, the oldest one will be deleted. There are 2 mutation operations in our algorithms. Add code to the key that represents architecture or delete code from it. The probability of selecting 2 operations is equal, and the number of codes added or deleted in one operation is from 1 to 4. Finally, we evaluate each architecture by 10 epochs and record its classification accuracy in the validation set. Then we select the architecture with the highest accuracy as the optimal architecture we find. We got competitive results in CVPR, and the generality of our algorithm has been proven in this competition. For 3 different datasets, we searched out 3 different architectures to complete the classification task with great results. And that concludes my presentation. Thank you.
Congratulations again to the winners. Unfortunately, due to issues that we had in competition, which postponed phase 3 by a week, it was a very tight turnaround time, so I do not believe that they were able to attend. But congratulations once again. So it's a bit early, but I think we now are. All right. Well, are there any questions about the competition first? Okay. In which case, yeah, I said it was a bit early, but we can now break for lunch and we'll turn at 1:30, where we will have our keynote speaker, Frank Hutter, give his talk.
Just as a reminder, if you want to join the mailing list, please use the first QR code. If you want to, or would like you to fill in either the paper form or the online form, just because we need to have a record of who's attending these events. Otherwise, the people who give us the money to organise the competition at this event will pull the plug. So we need a lot of names on that list, please. But apart from that, have a nice lunchtime, and we'll see you back here at 1:30 for Frank's talk. Thank you very much.
Hey, do you hear me? And see the screen?
I just had to find the unmute button. Yeah, I can see your screen. I can hear you.
Perfect. Good.
Right.
I guess we're all set for later.
So we'll hopefully be ready for just after lunch.
Great. Have a nice lunch. Thank you. Bye.
lunch. Just as I say, at every time, please consider filling in, or can you fill in the form? As I say, we need this to show to our university that it's worthwhile us coming to do this. There's also a paper version of that, there's the mailing list as well. We're going to start this afternoon with a talk by Frank Hutter, who is very significant in the AutoML community. He runs the AutoML conference, and he's kindly agreed to do a talk for us this afternoon. So are we ready for Frank?
Yeah, I think he looks ready. Are you ready, Frank?
Yeah, I'd be ready. And now I'm also allowed to share my screen.
Yes.
Right. Do you see the screen?
So I shall pass you over.
Excellent. Thank you very much for this invitation. Maybe just one quick question ahead of time. So in the end, people can ask questions. How does that work?
Oh, yes, there's an opportunity for questions at the end.
Perfect. Yeah, so thanks a lot for the invitation to give a talk here. I'm unfortunately not able to attend because I have 2 small kids, and yeah, but I envy you because I actually studied in Vancouver for 9 years and I love it, and a lot of friends there. So yeah, I hope you're enjoying your time there. So in this talk, I'd like to talk a little bit about something that's maybe not super popular in neural architecture search, namely black box neural architecture search, which is really, old-fashioned, slow, but it's a steady workhorse, and it's really versatile. So yeah, without further ado, let's jump into it. By the way, the slides are online. You can find them here, and all the references there are hyperlinks. So you can follow along and also look directly into the papers I'm referencing. All right, so let me start with a big picture motivation for what I call Deep Learning 2.0, which actually includes NAS as a centerpiece. So the motivation for, well, why did deep learning succeed in the first place was that, well, the traditional machine learning practice before deep learning had that the data directly, well, it goes into the domain expert, and the domain expert then actually needs to engineer these features, and then you can use traditional machine learning. And well, that of course resulted in a lot of trial and error, and deep learning allowed you to directly move from the data to the deep learning pipeline and automatically generate these features that would save manual labor and yield better results by an end-to-end joint optimization. So this joint optimization is importantly, you jointly learn the features here that then the final layers of the neural network can work well at. And that's a metaphor I'd like to use also for this, what I call Deep Learning 2.0. Now, Deep Learning 1.0 isn't quite as shiny here. So you're not directly going from the data to the deep learning. You still have an expert in the middle. Now it's a deep learning expert. It's not a domain expert anymore, but well, the domain experts over time sort of became deep learning experts. So a lot of computer vision folks are now just deep learning folks. And they, instead of engineering features, now they engineer architectures and hyperparameters and SSL pipelines and fine-tuning pipelines and so on and so forth. And then you can use this deep learning, but of course you still have this trial and error by this deep learning expert trying out all kinds of different things. And going to Deep Learning 2.0, I would like to also automate all these things, which again gives you the same type of benefits that deep learning gave over traditional machine learning. Namely, it saves human labor and it yields better results by an end-to-end joint optimization. So again, end-to-end. So you find the architecture and hyperparameters, etc., such that with those, the base level deep learning actually works well. Now, how could you implement Deep Learning 2.0? Well, it's by AutoML, of course, which is meta-level learning and optimization on top of a standard Deep Learning 1.0 pipeline. But that is not all. that's in my vision for deep learning 2.0. Otherwise, this would really just be AutoML. So deep learning 2.0 also takes into account that, well, deep learning 1.0 doesn't really optimize for all kinds of different objectives. It optimizes for cross entropy, and you need to worry about fairness, robustness, model calibration, latency, etc., etc. And because of that, actually, what I would like to have is for the domain expert that got lost when we went from traditional machine learning to deep learning to enter the picture again, to actually allow them to specify what do they actually care about. Do they care about cross entropy, or do they maybe care about a combination of accuracy and algorithmic fairness, etc.? And maybe we want to allow, like policymakers to define what is the right algorithmic fairness criterion to use in a particular context. And then that's part of our optimization problem here. Along with accuracy, you have this algorithmic fairness. And then what now changes to a multi-objective AutoML can still control the deep learning 1.0 pipeline to find the best trade-offs of the objectives that the domain expert actually cares about. And that then gives you the objectives that they care about by definition, by design. Note that we actually now have the domain expert in the picture, and the deep learning expert isn't in there again anymore, but it will come back in a little bit. But let me still remark on the fact that this deep learning 2.0 can really be paradigm changing and can democratize deep learning. You can actually carry out these deep learning 2.0 projects without a deep learning expert, and it directly optimizes for the user's objectives, leading to trustworthy AI by design. And that's why I think deep learning 2.0 will be even more pervasive than deep learning 1.0, with huge impact on the market. Now, I mentioned the deep learning expert not being part of this picture. I still think it's very important that they are optional in this picture because, well, these multi-objective AutoML techniques, if you actually know something about your machine learning model and about neural architectures and so on, then it ought to be possible to guide this multi-objective AutoML, to have human-in-the-loop AutoML, and that will get you much better performance. So if you have a deep learning expert, by all means, they will still be extremely helpful. And I think we should also look into methods more that actually do use this user knowledge and this expert knowledge. All right, so I talked about deep learning 2.0. This is a NAS workshop. So NAS is very core to deep learning 2.0. A lot of this picture, you could just write NAS in multi-objective NAS here. And NAS isn't everything because, well, hyperparameters are important, SSL pipeline are important, and so on. So it's really the entire pipeline that's important. But NAS is an integral part of that. Now, having said that, let me actually take a small step back and actually, as someone who very much cares about the field of NAS, have a bit of a critical look at the field of NAS because, well, it helps to take that perspective every now and then in order to come out stronger. So there have been over 2,000 papers published on NAS in the last 4 years. It's quite incredible growth of sort of exponential growth and sort of, converging here at around 600 papers per year. And we surveyed a lot of them in this recent survey here. But, well, so that might sound like NAS is super successful. And it is to some degree, but transformers and vision transformers and ConvNext and so on were actually discovered manually and not by neural architecture search. And that should get us worried. And I think if we take ourselves seriously, we should strive for the next generation of architectures, or maybe architectures in 5 years, to actually be discovered automatically and not manually anymore. It's also not really a focus of the NAS community to create robust and efficient AutoML systems. So what you would need for deep learning 2.0 is really, it's an AutoML system. And the NAS community looks by and large much more at, well, either coming up with some architecture that then can be used elsewhere in many different use cases, but mostly actually at, well, I have this particular hardware and this particular thing, and then I look at it a lot and I try these different NAS algorithms, and then I come up with an architecture. So really use it a lot more, yeah, in a maybe less automated fashion. And there's a lot of brittle algorithms that don't lend themselves well to be in an AutoML system that ought to be robust and usable by everyone. So with a little bit of a history here, in 2017 here, we had this neural architecture search with reinforcement learning paper that was extremely expensive, 800 GPUs for 2 weeks, just to get something good for CVPR 10. Then DARTS was fast, only taking something like 4 GPU days, but it had catastrophic failure modes, for example, leading to all skip connections. And then in the last couple of years, a very popular topic have been these zero-cost proxies. And they're unfortunately also not a silver bullet, because while they get you awesome performance within seconds on some search spaces, in other search spaces, they're just not correlated at all with performance, or at least not correlated more than trivial proxies such as number of parameters. And so that's why, at least it's not a silver bullet. It can be useful in some cases for sure. But after these 2000 papers, I'm still sort of wishing for, okay, this is our go-to method for, I don't know, for gradient-based neural architecture search. There have been a lot of possible replacements for DARTS, but sort of anything we use and try it on new search spaces, it doesn't really work incredibly well. And yeah, so maybe looking at these 3 possible use cases of NAS here. One is improvements of an existing architecture family. That is something that NAS, I think it's covering that hands down these days. So in small search spaces, for example, layer-wise hyperparameters such as a number of kernels and kernel sizes, on a particular type of hardware, for example, finding the right shape of the network. Okay, here you should use this many kernels, and this should be the kernel size in the first layer, this should be the kernel size in the second, the third layer, etc. There, I think, yeah, it's just everywhere in the industry. Everyone who's close to hardware is also doing a lot of work on hardware-aware neural architecture search. And nobody in their right mind would want to come up with the right architecture for all the 100 different Samsung devices or Bosch sensors, etc. And there it's very clear that hardware-aware NAS is the way to go, and that is very successful. One part where it's not actually that much used, as I mentioned, is really AutoML, given a new data set, robustly and efficiently make predictions. And well, that's just not a focus of the NAS community. And it is a focus of this lightweight NAS competition. So I very much like that you're running this. The winning solution today didn't really seem like it's very new, though. It was a variant of regularized evolution, which is an algorithm from, I don't know, 2019 or so. And so that sort of goes hand in hand with that. This is just not a focus. In some other fields, we would not have a winning solution from sort of 4 years ago. And I think maybe a little bit more people should work in that. And as a side note, maybe reviewers should also not completely discard the black box NAS direction, because because they think, well, one shot is faster and so on, but one shot is also more brittle. And I think we need to really make progress in all kinds of different NAS methods at the same time. Also, I mentioned transformers, VIT, etc., was discovered manually, and I think it's really we should try to take this seriously. Try to have this holy grail. We want to discover novel architectures with neural architecture search, and right now we're kind of tying our hands behind our backs. We're using very restrictive search spaces typically, where there's no way that we're going to find any novel architectures because, well, they're just not in the search space. The search space is just very tied to what we know works well, such that the search is efficient. But yeah, that doesn't allow us to really find novel architectures. And so in this talk, I want to really focus on these two parts here, having more like an AutoML type NAS system and trying to lay the foundations to actually work on discovering novel architectures by looking at novel types of search spaces. All right, so then without further ado, let me talk about some of the things that I will go concretely into. Since I will talk about black box optimization, I'd like to briefly talk about Bayesian optimization and how to speed it up with multi-fidelity optimization and meta-learning. And these will pop up in various shapes here. I think Bayesian optimization is in each of these individual papers. So these here are based on like one paper each. And multi-fidelity optimization occurs in several of them, and meta-learning also occurs in several of them. So first, I'll talk about some general methods, and then about some individual contributions. All right. So and the first part is then more tutorial style, and the second part is using some of these contributions. All right. So Bayesian optimization. Here is sort of the one-slide summary of Bayesian optimization. It is a prominent approach to optimize expensive black box functions. So an expensive black box function is a function where you can only control the inputs, and then you read out the outputs. And that's your only mode of interaction with it. It's a black box you can't look inside. And here's a visual depiction of this. So you have a true objective function here that depends on one hyperparameter that's on the x-axis, and the y-axis is, well, the true function value. And it's also a model fit. So we have a mean fit here, this black line, and these blue funnel, that's our uncertainty for our posterior distribution over what this function might look like, given that we have these two function evaluations. And then we use this model, this posterior predictive distribution, in order to compute a so-called acquisition function, and that's here in green. And this acquisition function judges how promising a particular configuration is, or a particular architecture in architecture search. I mean, this here is a continuous individual parameter just for the depiction, but the same approach works directly also for high-dimensional neural architecture spaces. I just can't draw them very well. So you then optimize this acquisition function, and this acquisition function always trades off exploration versus exploitation. So a simple one can, for example, be UCB, this upper confidence bound that just looks at sort of this upper envelope of my uncertainty estimation, so mean plus one standard deviation, for example. And so you maximize this acquisition function over the entire architecture space, and then you evaluate there. And you then have the true function value that was actually here, not up there. So you refit your model, especially locally, your model changes a lot. And then you re-optimize, you recompute your acquisition function, and now it looks like this, and you optimize it and evaluate at this point here next, and you iterate. And as you see, this is actually a quite sample efficient type of optimization that does quite a bit of work in between. But you know, if evaluating your architectures takes a certain amount of time, then it's fine to do a little bit of computation in between in order to think about what to evaluate next. Now, Bayesian optimization is efficient in the number of function evaluation. And it still works when our objective is non-convex, which is nice, noisy as algorithm runs are, when it has unknown derivatives, which is the case unless we backprop through our entire optimization trajectory, which we typically don't want to do. And it also has recent convergence results under certain assumptions on smoothness and so on that would unfortunately typically break in neural architecture search. But there is some theoretical foundation. All right, so that's Bayesian optimization. And Bayesian optimization has this one component of the surrogate model. So the standard surrogate model is a Gaussian process, which has a strong calibration, and it's mathematically a very convenient object. And one part of it is this kernel function. So this kernel function can be a pro and can be a con. You can modify this kernel function to really work for you, to be very customized to your particular application at hand. And when you do that, then you can actually get very nice performance. On the flip side is you kind of have to play with it in order to customize it to your application at hand. And two of the contributions I'll talk about later actually do use Bayesian optimization with particular types of kernels. Bayesian neural networks have been popular for a while, and of course, neural networks are super popular, and making them Bayesian is still something that people strive for. They are super flexible. Unfortunately, they're not so good when you only have few data points, unless you actually use in-context learning. So we have a recent paper now at ICML that does Bayesian optimization with prior data fitted networks. So where we do in-context learning in order to learn the surrogate model for Bayesian optimization. And that actually is a new state of the art for hyperparameter optimization, for black box hyperparameter optimization. And the third type of surrogate model that I will use once in one approach later on is random forests. And random forests, they're particularly nice because they're flexible out of the box. They deal with non-Gaussian noise, they deal with really high noise, etc. Really versatile. And so they're also a good off-the-shelf model. All right, so much for Bayesian optimization. Then let me briefly talk about multi-fidelity optimization. So the kind of key idea of multi-fidelity optimization is to use cheap approximations of the expensive black box. And here we're getting to the first speed up of black box optimization because, well, remember the RL for NAS, 800 GPUs for 2 weeks. That's not the type of compute we want to end up with. Actually, we want to end up with something that rivals one-shot optimization. And I will show you that that is attainable. But so what can these cheap approximations be? Well, they exist really in a lot of different applications. Trivially, in all of deep learning, when we have iterative training algorithms, then we can use fewer epochs with them, for example, like SGD. Everybody looks at their learning curve, and you can stop your learning early on, and that typically gives you a good indication of how well things are going. You could also use a subset of your data. You could downsample images. You could use shallower or slimmer neural nets. In Bayesian deep learning, you could have shorter MCMC chains. In deep reinforcement learning, you can have fewer trials, and so on and so forth. So it's really a versatile type of technology. And here's a particular example for it, where we actually use a subset of data for a support vector machine in this case on MNIST. So here we have the response value of the response surface of MNIST, where we have two hyperparameters, gamma and C here, and red is bad, and these blue ones are the best hyperparameters. And here we have the full data set, and here we have a fourth of the data set is 16s and 128. And note that these plots look very similar for the small data set and for the large data set, except that, well, the function evaluations here are more than 10,000 times cheaper than here. And so we can actually do a lot of work here and save computation over here. That's the idea of doing multi-fidelity optimization. So the idea is to do quite a few function evaluations here, and then not as many here, and less here, and maybe then just one here. And then we found the optimum for just sort of one expensive function evaluation and three, already much cheaper ones. And these are almost negligible in compute. And in fact, we've shown quite a while ago that you can actually get 1,000-fold speedups over black box optimization for SVMs. Now, when your fidelity is runtime, then this would look more like this. And actually, an algorithm that I also depicted here is basically successive halving, which randomly samples a bunch of configurations and then takes the best ones, in this case, the best third, evaluates them here, takes the best third, evaluate them here, takes the best third, evaluate them here. So that's successive halving in a nutshell. It's kind of successive thirding often. Here it's successive halving, so you drop half at each iteration and then you double the budget. So in this case, when the fidelity is a runtime, you let all of your random configurations that you sampled run to your lowest fidelity, then you drop the worst half, you continue the top half, then to the next fidelity here, you drop the next half, here drop the next half, and let the rest run. An extension of that also has theoretical guarantees is called hyperband. So that guards against situations like here when you actually have crossings of these learning curves. So if you were to cut off this algorithm early on, then you wouldn't realize that the green actually does surpass the purple one here. And so it might theoretically be the case that this blue one will actually just go on and go up here, probably not above 1, but above maybe the best one you've seen. And in order to guard it against that, basically what hyperband does is it increases this fidelity over its different rungs, doubles it, and there the fidelity is actually at the maximum. And so in this case here, in this quarter of its run, successive halving is actually identical to random search. And so as a corollary, successive halving cannot be more than a log factor slower than random search, but random search as such might not be extremely good. So that's it's a nice speed up trick. And if you compare hyperband against random search, then in particular, it's very good early on, because early on, actually, it can really save from these low fidelities, whereas later on, well, a quarter of its runtime is anyway spent on doing exactly the same as random search. So the speedups are not very large in the end. They're high in the beginning, not so high in the end. In contrast, Bayesian optimization in the beginning does not have any speedup, but later on it has a great speedup when it has figured out the search space and actually goes to the places that actually give you very good performance, whereas random search is just randomly picking things and is not exploring well in large search spaces. And you can also put the two together in this BO-HB algorithm, where you get 20-fold speedups in the beginning and sort of 50-fold speedups in the end. Somehow this didn't render well here. Okay, yeah. So so that gets you the best of both worlds. In the beginning, you're already very fast by this multi-fidelity approach, and later on, you still have this multi-fidelity approach, but you also have the gradient that you get from Bayesian optimization of just searching much faster than random search. All right, so much for multi-fidelity optimization and meta-learning. I could talk for 1.5 hours about meta-learning, but here's just the super short one slide, all that we need here. So there's a lot of different ways to do meta-learning across data sets. The one that's relevant here is we basically pre-train our surrogate model of Bayesian optimization across data sets. And that will be important in one of the approaches, in particular, the one that's coming up first here. So in this transfer NAS approach. Now, yeah, let's dive right into that. So yeah, this is an approach that actually, as a surrogate model for Bayesian optimization, there we use a Gaussian process, but we use a particular type of kernel, namely a kernel that is defined through a neural network. So again, the Gaussian processes have calibrated uncertainty and quantification. That's very nice. And they have strong performance with few samples. And the neural networks, well, they have the flexibility to learn meaningful features and scalability. And at a high level, we use the neural networks to learn embeddings for our inputs, and then Gaussian processes with a kernel function on top of these embeddings. In a little bit more detail, we have a surrogate model that has a embedding for for our data sets. And then we have an embedding for our architectures. So for the data sets, our embedding is actually, we use a transformer for it. For the architecture, we use a graph neural network. And then we fit a kernel on the concatenation of these embeddings. So visually, we have a data set here. We have a data set encoding, we have an architecture encoding, and then a joint encoding. And this is meta-learned across a previous set of all kinds of architectures running on all kinds of data sets. We're learning these encodings, phi, psi, xi. And once we have these encodings, then it's just a matter of fitting a Gaussian process on there and running Bayesian optimization. And so the hard work is really in the meta training of these embeddings. So the rest of the pipeline, the experimental setup, we actually took from this really nice paper, Rapid NAS from Heon Lee et al. So what she did is to define 4,230 subtasks of a downsampled ImageNet with 20 classes each. And so train on that. And then as test data, we also use the same as Rapid NAS, namely 6 different image recognition data sets. It's a search space. We also, like Rapid NAS, use NAS Bench 201. But here, actually, in preparing the slides, I must just say that is a weakness of this paper. We only use NAS Bench 201. We have no guarantee that this also works for general search spaces. I do expect that it does, but really that is left to be shown. The rest of the pipeline, we just use standard Bayesian optimization for up to just 30 function evaluations, not the, 20,000 or something like that, RL for NAS used back then. And we use these deep GPs based on this meta-learned combined kernel. And whenever we have a function evaluation, then we fine-tune the embeddings after we got the function evaluation. So we fine-tune on all of these once we have a new function evaluation, because the new function evaluation is so important that we definitely want to fine-tune to this, and a little bit of cost from fine-tuning is negligible compared to an evaluation of a full architecture. All right, an evaluation of the architecture as in you train the architecture from scratch and then see how well it does. All right, so that's the methodology of this paper. The results for this paper for these 6 different benchmarks, results over time. So here these are GPU hours on the x-axis. You see that this blue curve transfer NAS starts going up pretty quickly, and in all cases, in the end, is actually at the top. Some of the competitors, well, here's random search. One should have that in there just to see that, yes, you're better than random search. Gaussian processes with UCB are also quite often quite strong. Then we have bananas. That's a Bayesian optimization with neural networks. We have NASBOL that uses a Weisfeiler-Lehmann kernel. And I have an extension of that later on. Hibo won the black box optimization competition at NeurIPS 2021, I think. And it's a very nice approach. It has a few issues with discrete parameters. That's why it's not actually that strong here. And the encoding here for the architecture there is discrete. And well, this transfer NAS is actually much better and very robust. So robustness in terms of its rank, in the end, it's just rank 1, whereas all the other approaches are sort of mixed. And while here I only talked about baselines that are based on black box optimization, here I also have baselines from one-shot NAS, so GDAS, PCDARS, DRNAS, ZN, and also rapid NAS. So that's this meta D-tray. And yeah, we see that still the rank of TNAS is number 1 on all of the cases. And over time, so here's a plot over time, we see that, yeah, already after a couple of GPU hours, its rank is on average the best. The one-shot methods, yeah, they're sort of all over the place, not actually as strong as the black box optimization methods. When yeah, when you're actually tackling a new data set, then often one-shot NAS has its issues. All right, good. So I'll leave it at that. Normally I would kind of ask if there is any questions for this, but I think I'll take questions in the end, just for reasons of the online talk. All right, next up is another topic that's hierarchical spaces, and I've motivated these quite a bit by actually discovering fully new architectures. Let me very briefly talk about some architectural search spaces. So there's this very standard linear space that's actually used in MobileNet, for example. Then there's more complex spaces with multiple branches and skip connections and so on. And then there's cell search spaces that fit sort of multiple of these, or one or multiple of these cells that are these more complex architectures, and then puts them together into a new architecture. So this part here occurs here and here in this architecture, and this part occurs here, and typically this reduction cell that occurs a couple of times in an architecture, and this maybe 20 times or so. So you just stack them up. And this was it was kind of a breakthrough back then. There's a paper by Beresov et al. At CVPR, and that was the year after RL for NAS, and this here actually then allowed you to come up with architectures for example, CFAR, and use exactly the same cell and plug them into a different macro architecture for ImageNet. But while this was really a breakthrough, and that's what led to everybody jumping on these cell search spaces, and then everybody's using these cell search spaces, and that doesn't allow us to actually really find new architectures, because the cell search space is typically quite limited in what it can express. And hierarchical spaces can express a lot more. They kind of use the same principle of the cell search space, that you have these building blocks that are used in multiple places of the architecture, but you can actually do this. You can reuse these substructures on many different levels. You can have these, you can do this recursively. You can have choices on many different levels. And there's some examples of this in the literature, but I really feel it's a much understudied direction. And just to motivate it a bit more, I mentioned transformers earlier. Well, transformers you could actually see as an element of such a hierarchical space. So you all know this architecture plot. You have a multi-head self-attention, or the multi-head self-attention, that is itself an architecture. And that, for example, has a scaled product attention in there. Well, that itself is an architecture. And so you could actually break down the pieces of a transformer through a hierarchical decomposition into and write a search space where you would say, well, I have a search space on a low level. I want to hook up my different components like this, and then I'm going to reuse this component there, and I'm going to have these parts around it. I'm going to reuse this component here, and edit it a little bit in here. And then all the rest is actually quite simple. It's add a norm. So that's just a, the skip connection and the layer norm. You can also put that here. The pre-norm that actually tends to work a little bit better. Then feed forward. So all of the other components here are actually relatively benign. And so the biggest thing here is really this multi-head self-attention and how that is combined out of different building blocks. And so we haven't done this. This would be expensive to search in such a space and to evaluate transformers, and that is one of the reasons that people just haven't really looked at extremely complex search spaces for extremely complex problems, because, well, then the costs just get too big. So I think we want to make methodological advances in thinking about really complex spaces, but evaluating them on tasks that are actually cheap to evaluate. And so that's what we did in this work here. In this work, we presented a new way of actually writing hierarchical search spaces, and in particular formulate them as context-free grammars. So this is done by actually making choices on multiple levels of the architecture that can be described by context-free grammars. So at each level, we can apply a so-called production rule in this grammar to add some more detail. An example will help, I think. So we start at the starting symbol S, and we have a production rule that says, well, S could be one example of that. S could be a linear architecture. And there is an S again. So it's recursive. This S could then again be a linear, or it could also now be a residual, but here is a linear. This residual again has an SSS in there. Well, this S here could be a conf, this could be an ID identity, this could be a conf, etc. And then you see how slowly you just add more and more detail to this architecture as you go deeper in the levels. Here is the NAS bench 201 space written in such a form. Well, the red part is the NAS bench 201, where you just have a cell that has 6 different operations. These are the operations, and the activation is ReLU. You have these choices for convolutions, and the norm is batch. And then in brown, you could just, for example, now add a couple of additional activation functions, or another type of convolution, or some other types of norms into this grammar. And you could also do something that's going to look fairly daunting. Can put a macro architecture on top. And I'm not going to explain this in detail, but when we did that, and then the resulting search space actually here now has a 10 to the 426 architectures, where the red part just has something, what was it, 15,000 architectures. So you can express extremely complex architectures with these context-free grammars, and well, this grows exponentially. And then the question is, well, how do you actually search in these massive spaces? Can we search there? And so then we also came up with a Bayesian optimization strategy with a special kernel for these types of hierarchical spaces. We used the Weisfeld and Illman kernel that's also used in NASBOL. But we also took into account that we have this hierarchical structure, and then applied a Weisfeld and Illman kernel for each of our levels of abstraction. So if you have an architecture like this, we would apply Weisfeld and Illman kernel to that, but then also to an abstraction like this, and also to an abstraction like that. So basically at each of the levels of the architecture, we could look at what is a super big picture of the architecture and what is a more detailed picture of the architecture. And we also had a mechanism to foster regularity by substituting different pieces. So reusing partial architectures at multiple places in the architecture. And even the reused architecture could itself contain other reused parts and so on. And this could be a recursive process in principle as well. So it's a very interesting and expressive way of writing search spaces. And we have a lot of different examples in the appendix of the paper. There's sort of how can you write sort of all the search spaces out there, all the popular ones as these grammars. And we did experiments primarily with this hierarchical NAS bench 201 space, but also with some other search spaces. But for this one, we actually used 5 different types of data sets, CVPR 100, and ImageNet. So these ones are from the NAS bench 201. And there, actually, in many cases, it worked similarly well as previous approaches. But then we also used 2 other data sets that came from previous competitions and that are not heavily studied in the NAS literature. And there we got particularly strong improvements. So in this slide here, you see improvements everywhere that for our particular search space, this Bayesian optimization with this hierarchical Weisweiler-Lehmann kernel actually does clearly best. But also when you look at compare it to the standard NAS bench 201 training pipeline on the NAS bench 201 space, it also, with the same time budget of up to 100 evaluations, it already does better than previous best result in any of these spaces. For CVPR 10, 100, and so on, not that much, but for some of these newer ones, actually even more so, because they haven't been optimized as much by the community. We also looked at other search spaces, and actually including activation function search. So there's a Swish paper from Corkley's group that does, I think, regularized evolution, or RL, but I think regularized evolution in the space of activation functions. And so they found something that had this performance of 8.61 on CVPR 10 with a cheap training pipeline that's quite so bad. And we found something that's actually a fair bit better. We don't need the hierarchical Weisweiler-Lehmann kernel here. We also just a standard Weisweiler-Lehmann also does almost as well. But both of them actually do better than this previous regularized evolution approach. So this goes to show the versatility of this approach of you can write NAS bench 201, make it hierarchical, write activation function search spaces, etc. So I'd encourage you to try it out and give us feedback. And the link to the paper and the code is here. All right. Talking about versatility, and so these 2 points here are actually very short. You can also include hyperparameters and make it multi-objective. So this hyperparameter paper, this here is just a benchmark paper. Hyperparameters are really important. As we've seen in this NAS evaluation, is frustratingly hard paper. So in this JAWS bench 201 paper, we have 4 different hyperparameters, and also the NAS bench 201 space, but also different fidelities to do multi-fidelity evaluations. We have lots of evaluations. So if you want to play with neural architecture search spaces with performance data, we have 140 million performance data points in this one. And let me just mention, so adding hyperparameters into NAS, it's really impossible for some NAS approaches. So I wouldn't know how to do it for one-shot NAS. For zero-cost proxies, sort of by definition, they're about the architecture, not about the hyperparameters. So you can't do it here, but it's really trivial for black box NAS. You simply extend the search space by hyperparameters, and then you do BO over this joint space of architectures and hyperparameters. And the last point is, yeah, you can then also make this multi-objective, so closing the loop to deep learning 2.0 to add another objective function here, in particular fairness, algorithmic fairness and face recognition. So this is a case study. It's motivated by the fact that face recognition systems are known to exhibit bias in different socio-demographic dimensions like gender and race. So darker males, you get fairly good performance. Darker females, you get the worst performance. Lighter males, that's a typical bias. You get the best performance, and lighter females also not that great. And why is this a problem? Well, face recognition is used in a lot of ways by law enforcement agencies, for example, for sensitive applications, identifying suspects, tracking down missing persons, biometric security, etc. So you want this to work similarly well for everyone. And unfortunately, traditional approaches like pre-processing, different trainings, post-processing methods for this instilling algorithmic fairness have actually failed to close this gap. And we asked ourselves whether deep learning 2.0 can help. And in particular, what we did is, well, we used LFA and had the protected attribute gender, had a particular fairness metric, and then looked at different architectures and different hyperparameters and just looked at how good are they in terms of bias and error. And then designed a search space around the best model and ran NAS and HBO to discover new architectures that sort of did better than all the other architectures, and Pareto dominated them. I think I would actually like to leave a bit of time for questions, so I think I'll skip over over the details here. But while this here was just a cartoon, the real data doesn't look much different. The architectural space, I skip over that. We used SMAC, which is a popular Bayesian optimization package that does multi-fidelity, multi-objective. And these are our discovered architectures from SMAC compared to these best other architectures. And this also generalizes to other fairness tasks, interestingly enough. So these architectures and hyperparameters are truly just more fair than others. Even if you change now to perceived gender or to perceived ethnicity, they still continue to work well. All right, with that, I'm at the end. So the takeaways are that deep learning 2.0, it's expert guided automated deep learning for the objectives at hand. NAS is a very integral part of that. And well, I reminded myself in creating this talk that black box NAS can also be pretty cool. And we can actually use it to power deep learning 2.0. Its speed can rival one-shot methods, and it's very flexible. I wouldn't know how to address these hierarchical search spaces with one-shot methods. Yeah, hyperparameters naturally integrate. And yeah, we can do multi-objective, joint architecture, and hyperparameters search as well. All right, thank you very much. And I'm looking for questions. Oh, looking forward to questions. But before, we're running the AutoML conference, so I very much invite all of you to get involved there. It's in Berlin in September. So yeah, looking forward to seeing some of you in person there. All right. And
thank you very much.
Right. Questions?
Frank. David, do you want to do that because the microphone for Frank is on your laptop?
Yeah, true. All right, so I do actually have two questions for you about your talk. So the first one actually is about, because you're saying that JARS includes hyperparameters. So I think I mentioned this earlier, which is a lot of NAS methods. They find their model first and then train hyperparameters afterwards. However, what me and Steve and a few others are very much wanting to look into is integrating that into the search process. And so I was just wondering of how does JARS handle the hyperparameters? Does it do it while it's training, or is it after a model has been found?
Right. Yeah, so I mean, JARS is just a problem formulation. It's but it stands for Joint Architecture and Hyperparameter Search, and indeed it emphasizes the joint aspect. So I previously also sometimes we called it Joint NAS and HPO, but Joint NAS and HPO is sort of just lengthy, and so we started calling it JARS now. But yeah, in a nutshell, it does it simultaneously, and it's really simple for black box approaches. So it's as easy as this. So basically, you have a search space. Say you have NAS page 201. It's a very simple search space, of course. That's just basically 5 categorical decisions, and then you have another, I don't know, 10 hyperparameters or 1 hyperparameter, and it's now not a 5-dimensional space, but a 6-dimensional space if you have 1 hyperparameter, or a 15-dimensional space if you have 10 hyperparameters. And Bayesian optimization kind of doesn't care so much. Bayesian optimization has its issues when you get to high dimensions like 20, 30, but there's also fixes for that. And I mean, of course, you can run one-shot NAS or some other approach just for the architecture, and then do hyperparameter optimization with some multi-fidelity BO, etc. afterwards. But in some cases, you can also just do it jointly, and I think we're pushing the boundary more and more with this multi-fidelity optimization, with meta learning, etc. That I hope we can more and more get to the point where you can simply just optimize it jointly. And that's what we did here.
Yeah, that's great, thank you. So my second question is, so part of your talk was about mentioning how a lot of NAS use restricted search spaces. In fact, you've created a very big and large search space, and that's a part of your DL 2.0.
It's true. Let me, before you go on, let me clear up one misunderstanding of reviewers in a previous version. It's not just about a single search space. It's really about a way of generating search spaces by means of this grammars. You can write search spaces much more concisely and quite conveniently. And then we did a lot of examples on this one particular type of search space, but it's not just this one. Sorry, but go on.
Right, so, but I was asking, so what I wanted to ask was, so previous work that we did in last year's workshop was SpiderNet, where it grows its search space, so it doesn't start with it doesn't start with like a set structure, it grows as it goes. I was wondering if you have any comment of how that fits into the deep learning 2.0, this like sense of growing a search space.
I think that's a very good question. I think just directly here, you could think of production rules that are added over time. So for example, you could start with only the red and then also throw in some of these as you go. More generally for deep learning 2.0, yeah, I think absolutely. Let me say I have to go back quite a bit. Oh, come on. Yeah, so here it basically is all about, well, there's this deep learning 1.0, and this here parameterizes the deep learning 1.0, and this part here could by all means decide that in order, for example, to get a good performance quite quickly, it starts with a very benign architecture space, and over time it grows it in order to home into the promising areas. I think that's actually a very nice approach. I think I haven't actually read the paper, but it's, yeah, I think there's a lot in terms of intuition, there's a lot going for it. We have one approach that's called SERL. That was in the context of reinforcement learning, but it was also adapting the architecture over time. And we use network morphisms to grow the architecture over time. Is that also what Spider does, or?
So I can't remember exactly what type, the basic structure of it is you start with a few nodes and it creates right-handed joint connections, and it has a mutation algorithm which adds them over time and uses differentiable pruners to remove bad connections. So it will chance a new one. If it performs well, it will keep it, but if it performs bad, it will then remove it while adding new ones throughout its generation.
That sounds great. Should look at it. Do you have code to play with?
What was that, sorry?
Do you have code for it to play with? I think
I believe there is code available. I'd be happy to send you an email of it afterwards.
Cool, thank you.
Brilliant. Do we have any further questions? Any other questions from anybody? Yeah, do you want to come up, because Frank will only hear you if you put the laptop.
Yeah, hi. I have a concern and then a question. So you said by using the web phase 360M data set, I think 320 plus models were trained and experimented to figure out which is the best model. But isn't that practically not feasible? Because I think the data set is quite huge and the models are quite big. So instead, what I would prefer is something. Does AutoML also support something I train one network, and can it suggest me, or can it figure out the dead channels and unused skip connections and stuff to reduce the number of parameters?
Yeah, so I mean, deep learning 2.0 and AutoML, these are just very generic terms that are all encompassing pretty much. So you could absolutely say, yeah, this here is allowed to do all kinds of pruning and so on, and start with a big network and then do differentiable pruning, etc. The first part of your question, I must say, I didn't fully get. Was it in the transfer NAS or?
That's a concern, because I work for a face recognition company, and we training a single network already with the best of the GPUs takes with our data set almost a week or more than a week. So if I have to try 300 plus models, I think that's almost impossible.
Yes, I mean, and that's where I was going with saying, so in this paper in the hierarchical NAS, here we didn't do any meta learning. We didn't do any multi-fidelity optimization because we actually didn't need it. If we needed it, we could make it 100 times faster, just like we did in transfer NAS, which is actually faster than one-shot NAS by meta learning. Here we used 100 full function evaluations because there are actually a lot of applications out there where you work with a particular sensor. You have 10,000 data points. You just want the right architecture for this particular sensor for particular hardware, and you can solve it in a few minutes, in an hour. I think that's a field we haven't really focused on at all with neural architecture search, and I think we should also cover that field. And I think by coming up in an automated fashion with really novel architectures for such cheap cases, we will lay the foundation to then also come up with novel architectures for the expensive cases. And of course, for the expensive cases where things take a week, we need all kinds of meta learning, multi-fidelity optimization, and the full the full thing in order to get anywhere. I mean, we can't just say, oh, look, here you have 10 to the 500 architectures in the space, go have fun. Even if our efficient methods take only 100 or 1,000 function evaluations, that's completely impossible. And, also very interested in transformer tuning and so on. And GPT-3, $5 million bucks. It's yeah, you're not going to do a lot of function evaluations, and you're not going to start with full hierarchical spaces for GPT-3. But maybe you come up with hierarchical search spaces for GPT-1 and then have an objective function that actually rewards good scaling behavior, etc. But if we just tie our hands behind our back, we're never going to find architectures in an automated fashion that are really novel. And well, the next transformer is going to be found manually again. And it is part of my ambition with AutoML to also help experts to really find novel, better architectures as well. So I hope that answers that question partly.
Yes, yeah, that I am pretty much convinced. But the question that I had, does the AutoML library, so if I have a trained network, so does it optimize the trained network? Does it do it already?
And the answer is there is no AutoML library. Sorry, we have NASLib. NASLib has a lot of different things in there. It has all kinds of zero proxies. It has a bunch of one-shot methods. It doesn't have pruning. It has like the 35 different performance predictors, etc. But I'm not pitching a particular library here. Like AutoML, it's a conference. Like there's machine learning library.
I think I used the wrong word then. Yeah. Sorry. Yeah. Thank you.
Thank you.
Brilliant. Thank you very much. Yeah. You're going to need to come up because your microphone might Frank can hear from this one.
Hi, sorry, I just caught the ending of your presentation. I just have a question, I guess, in the future direction for NAS. We know that search space, keeping the search space large is really important, but there is the significant time cost when we do that. I was wondering if you considered any, let's say, distillation on the data that could potentially reduce the training time so you could retain a larger search space without necessarily impacting like the proxy performance for the models.
Mm-hmm. Yeah.
Yeah.
So there is this paper on generative teaching networks by Jeff Kuhn that does some distillation for NAS. We played around with it a bit. We didn't really get it to the point where it was speeding up things. But if you only got the end, then you might have missed this transfer NAS where yeah, it is actually faster than one-shot methods if you do meta learning. So you meta learn across architectures and across data sets on previous architecture data set pairs. And then when you do that, then given a new data set, your surrogate model can directly propose a very strong architecture for this new data set at hand. And you get away with very few function evaluations. Like here, it's basically a couple until you hit the optimum.
Okay, that makes sense. I'll check out that paper for sure. Yeah, thank you.
Thank you.
Brilliant. Thank you very much, Frank. And we give one last round of applause. I'm sure that Frank will be available. He's got his automl.org website, and I'm sure you can find his email address so if you have any further questions. So thank you very much, Frank.
Thank you very much.
And without further ado, I think we're now moving back to the papers.
Yeah, yes. So the next paper, just need to skip past this, is paper 3 by Yifan Huang. So we have a video to play. I do believe we have someone from the team to ask questions after the video. So we'll bring you up once the video is finished. And I'm just going to make sure that I am streaming this on Zoom.
Hello, everyone. My name is Wintao. Thank you so much for attending my presentation. I will talk auto short, short video dataset, and the state-of-the-art short boundary detection. So what is the video short boundary detection? This is a thumbnail image. So you can see, you can see here there's a scene change here. So here there's a white bar used for this two short segmentation. And the second shot is from here to here. You can see there's a color change, a huge color change, significant color change here. So there's a blue bar here to annotate this short change. And the third one is here. You can see it's pretty clear from this shot to a dark shot. So there's a white bar here to annotate the shot. So all this work, the data and the code models are publicly available. So you can access from the GitHub, or you can scan here to access the repository. So these are contributions for the worker. So first is that we try to, the motivation is that there's an explosive popularity of short form videos. There are several these mainstream short video platforms such as Quail Technology, TikTok, Instagram Reels, YouTube Shorts, etc. So which means there's a significant need for the video content creation and understanding. Behind this, the fundamental technique is the short boundary detection. So to serve this goal, we collect a new dataset called the short, which is a new public short boundary detection dataset. So we collect about 1,000 short videos, and this dataset has about 12K shorts, and where there are 200 test videos with about 3K high quality this boundary annotation. On top of this dataset, we propose a new method called AutoShort. And AutoShort uses the neural architecture search, and we constructed the search space based on various three-dimensional convolutional neural networks and transformers. So this the AutoShort, the search the architecture outperformance translatively to previous state-of-the-art by 4.2% on the collected short video dataset based on the F1 score. We validated the generalization for the search architecture. The search architecture outperforms the previous state-of-the-art over 1% on all the three public datasets based on the F1 score. So this is the outline. So we will first talk this motivation, related work, and the dataset, the methodology, experiment, and the conclusion. The motivation of the work is that we find that the short form videos have been widely digested among the entire age groups all over the world. So because of its richer content, better delivery, and more persuasive effects. So there's an urgent demand for temporally accurate and comprehensive video analysis. So the fundamental technique behind the video analysis and the intelligent creation is the short boundary detection. So SBD in short. So it is the basic block for many video related tasks like this scene analyze, video structure, and the event segmentation, etc. So previously there are also some more laboriously annotated datasets, but basically they are these datasets target on the long form videos. The BBC and the RAI only consists of documentaries and talk shows. So which means the scenes are relatively static. There's also one large dataset called clip shots, and which focus on the long form videos. These are the comparisons among this dataset. You can see the first three, BBC, RI, clip shots, are the conventional dataset. So there are no complicated gradual transitions, no virtual scene, no tutorial videos, and the average video lengths are pretty large compared with the short video in the short dataset. So you can see it's about 10x longer than the short video. So which in turn leads to the shorter average short length. You can see here in the short video, the averagely the 2.6 seconds, there will be a short transition. But in the conventional dataset, they are about 10 seconds. We will have a detailed analysis in the following slides. So these are several challenges for the short video related boundary detection. So in the first row, you can see it has a combination of several complicated gradual transition. Gradual transition is the most difficult this transition to detect. The second one is a pretty huge a quick transition. You can see from here. And the third one is that the view effect in these game videos is very complicated. So the right one is this video length and the short length analyze between the clip shot and our collected short video. So you can see from the video length, there's no overlap. From this each single boundary statistics, you can see our the short video. This is the average short length is the distribution, the property is far from the previous clip short dataset. So our contribution is that we first we collect this short video dataset. They are about 1K short videos and 12K boundary annotations. So this is as far as I know, this is the first dataset for the short video short boundary detection. And on top of it, we develop this auto short, which is auto ML for the video short boundary detection. So we use neural arterial search. And for the search space design, we propose various advanced three-dimensional convolution networks and transformers. So as far as I know, this auto short is the first specially designed neural arterial search method for the video boundary detection. So and auto short beats the previous state of art on the F1 score. You can see on the search dataset it outperforms previous SOTA by 4.2%. And we also validated the generalization ability for the search architecture. So you can see without searches, so there are over 1% on all the three public datasets. So previous work for the video boundary detection, the most popular one is the pacing detector, which is based on the conventional features, this color change between frames. And for the deep learning one, deep learning based this boundary detection, there are deep SBD, use the deep spatial temporal convolution network, and deep structured model use a cascade framework to accelerate the speed the translate use dilated convolution, and translate V2 use this convolutional factorization escape connection to further improve the accuracy. And there's one contrastive self-supervised learning to learn this short representation. Okay, let's discuss this the data set. So you can see we find that it's pretty challenging to conduct this boundary detection on the short video. Because of the nature of the short video, the video length is pretty short, which leads to a fast pace of events. So which means the short boundary detection is pretty difficult for the short videos and the rapid short transition. So you can see the first row. So this is clearly a short transition, but it has a complicated. It's a combination of complicated short gradual transitions. And the second one is the vertically ternary structured videos. So yeah, so basically there's no change in the up and the bottom, so which consists of two-thirds part of the content. So if we use this conventional short boundary detection algorithm, we can't detect the change because of this small region, but actually it is the actual content for this video. The third one is for the game video. The intro short change is greatly, so which means it may have many false positives. So to achieve the goal, we collect 1K short videos, which have about 1 million frames. So we conduct a rigorous auditing process, and we control the error rate to be lower than 2%. For the test set, we check several times in order to be valid for the evaluation. You can scan here to download this dataset. So for the on top of this dataset, we develop a methodology called the auto short. For the search space design, we develop four three-dimensional convolutional network. The first one is the spatial convolution, followed by the temporal convolution. The second one is the shared spatial convolution. Third one is the parallel design of spatial convolution and temporal convolution. This one we use the residual design for this shared convolution plus the temporal design, because we have several layers of blocks. So maybe in the first block definitely we try to extract more abundant of these special features, but probably in the later stage there's no much need for this special convolution. So this search can get a much more high accurate architecture. So for these architectures, we conduct this channel number search, and also we add the transformer their number search. So in total, we have about 1 gig candidate architectures. So for the search, we use the SuperNet single pass one-shot algorithm, the Bayesian optimization search, the Gaussian process, this surrogate function, and the acquisition function. So you can find the detailed optimization, the search detail from the paper. For the loss function, we use the cross-entropy loss for this structured segmentation. So here there's there's one trick here, that is we use the middle frame, which is middle frame of a transition, which is definitely pretty robust and accurate. And we also use this all transition for the gradual transition. In that way, for the gradual transition, this all transition is much more accurate. And we use the knowledge distillation to further improve the accuracy. You will find it is pretty useful in the experiment part. And we use the other technique called wet grafting. This way we can extract this feature from all the networks, but without this actual computation requirement. So these are hyperparameters. All the code and the data are available from this link, the GitHub, and you can scan here. So okay, so but I want to stress that for this work we use the 8 GPUs. That is totally enough for this work. So we conducted the neural test search on the collected short data set. So you can see we get the 4.2% improvement on the F1 score. And we also validate if we fix the recall rate, we find that our model improve the precision, the accuracy. We improve 3.5% than previous SOTA. After we finish the search, we directly use the search the architecture and validate the generalization on the other 3 dataset. So and we use the previous experimental protocol. We achieve this improvement consistently. So we also we design 3 space, and we find that this auto shot the large most this 3 space has the highest accuracy. We find that this large 3 space indeed is pretty helpful. And also the knowledge distillation, you can find if we use the knowledge distillation, we can shrink this F1 range, and further we use the wet grafting so that we can extract these useful features from all these architectures. So that the wet grafting is pretty helpful here. So we calculated these G flops. So you can see if we search based on the F1 score, we have the 37 gig max, and if we search based on the precision, we have the architecture has 30 gig max. Previous state of art, the Transcend V2 has 41 gig max. So which means our search which means we don't increase any complexity. So yeah, we don't have any increase any complexity. So this is the visualization, the results you can see. You can see we use different color to annotate this false positive for the previous SOTA Transcend V2 and auto shot. So you can find the details from the paper and the supplementary. So basically, our work can have a much accurate than previous state of art. So okay, so in this work we first collect a new short video boundary detection dataset to accelerate the development and evaluation of different video applications, and we developed neural arterial search for the video boundary detection. So in the 3 space, we propose several advanced 3-dimensional convolutional network and transformer. So our algorithm surpassed previous state of art by over 4%, and also our method is pretty generalized pretty well. So thank you so much for attention. So if you like our work, please scan here to get the data and code and the models. Thank you so much.
Brilliant. Thank you very much. So you're able to take some questions on this. Do you want to take the microphone there? Do we have any questions? So in a sense, I think it's great because we are lacking in decent data sets for neural architecture search. But what kind of drove you to actually, because I mean, a lot of people generate data sets to just do deep learning on. What drove you to do it as a neural architecture search problem?
Oh, how our work can be helpful to the neural architecture community.
Yeah.
Yeah, thank you for this question. I think I think this is definitely a great question. So I think to understand this question, so I think first definitely this is a very great application. So because as you can see, my previous so currently I work in Amazon. Previously I work in the Quattro Technology short video. It is the second most largest short video platform company, and also IPO in the Hong Kong server market. So so this project is sponsored by the Video Ads Creation. So because there are many, so if this advertiser provides the like 2 minutes video, the ads video, but actually for the user probably we only attend to the focus on the 30 or 15 seconds. So we should create an intelligent this content creation algorithm, try to reduce the video length from the 2 minutes, maybe 3 minutes to the 15 or 30 seconds. So it has a very big business value, and so I think for the other aspect, I think for this question is that so to make the impact of this algorithm, the other ways that we try to have a pretty high impact this application. That's also the other way. So as you can see, this in the video boundary detection. So definitely this work is much better than previous SOTA, so yeah. So from the methodology itself, I can say so here there are several takeaways. So the first is that you can see here, I think is that we successfully apply this neural architecture to the video understanding community, which is definitely very great because so you can see a lot of work on the to try to use the image data, but now you can see it is also it is also applicable to the video community, because video consumes a lot of resources. And the other is that you can see this knowledge distillation, the wet grafting. So and also some inside here, the large search space helpful. So so I think the takeaway is that try to design large search space. Try to you can also use the knowledge distillation, because typically in the search space, so there are many architectures may have different performance, and if you use knowledge distillation, you can improve this performance to a higher range, higher accuracy, and then you can use the wet grafting, so that the final performance is like assemble, but the wet grafting only generate a single architecture, so which is great because you can't use many ensemble for the real product, but you can use one architecture to get for your application for algorithm. So I think that is a good way to use to leverage this neural arterial search to leverage leverage the neural arterial search.
Brilliant.
Thank you.
Any further questions? In which case, oh, sorry, I missed.
How did you decide to design the search space?
Oh.
What goes into selecting the different ranges of parameters that you chose? And then in the interest of automating this kind of process, could you see a way that you could have maybe automated that selection of the search space?
Automated search space. Yeah, that's a very good question. So I totally understand the question. So your question is how to automate the search space.
Well, I guess my first question is how did you decide how to parameterize that range of values? And then could you imagine a way of automating that selection?
Yeah, the insight. So first is insight. Second is how to try to automate the process. The insight is that as probably I just use one sentence in the presentation. So I think the first is that because you can see typically if we understand a video, so the first stage definitely we want to stress this special understanding in the first stage. Later on probably we will, after the fully understanding of the special information from each frame. So in the later stage, probably we want to emphasize this temporal information. And so you can see from our search space, so we have different architecture to balance this spatial learning and temporal learning. And neural arterial search definitely is a great tool. Try to find the optimal optimal design from different layers, and you can. I think in the we also do the analyze in the search architecture. So it's exactly in the so you can we design 4 different convolutional 3D variants. So so you can see from there. Some architecture we use more on we focus more on this spatial learning, and also some we just use shared spatial learning. There will be more parameter on the temporal learning. So and finally in the search architecture, so you can also find in the first few layers it's we try to use more parameters on the spatial learning. And later on, there will be probably use the shared spatial learning. So it is the inside of the search space design. The how to automate this process is I think so for this work we definitely we didn't tap this direction. So but I think that's a pretty interesting topic. So so yeah, I think that's a very good research topic to work on. Really, it's and that's a very good research topic to work on. Thank you so much for your question.
Brilliant, thank you very much. So I think we're moving now into a break. Ooh. Yeah.
This slide is not up to date.
Yes.
I just realized.
Is that 3:30? It should be.
Yes. So we'll be reconvening at 3:30. I'll change the slide in just a minute.
And just while I remember, because I'm always happy to say this, because otherwise we say we don't get to do it next year. Please join the mailing list, but also either physically fill in the form that's on the table there, or fill in the online form that we'll put the QR code up for in a moment when Dave fixes the slides.
Yeah.
Just so that we've got something to prove to people that people actually turn up to our workshop and it's worth sending people to.
And during this break, we ask the remaining paper authors, that is Ryosuke Yamada, Risa Shinoda, Lottie Hendricks, Yu Hao Chen, Yongguo, and Lujun Li. If you're in the room or on Zoom, can you please let us know so we know how you want to give your presentation. And if Dongming Ma is still here, I think you've left your memory stick. But yeah, so.
But apart from that, you've got 15 minutes of break.
Yeah. right, so welcome everyone back. So this is the final break. That's the final break. So now we have the 5 remaining papers. So first up, we have the paper from Ryosuke Yamada and Risa Shinoda on exploring the potential of neural data set search. So I'm just going to get this ready for you. Where? Sweet. Right.
Hello, we are introducing our research, exploring the potential of neural dataset search. Firstly, deep neural networks plays a crucial role in computer vision. Deep layers achieve high performance for image recognition and solving various tasks such as classification, segmentation, and detection. However, alongside these benefits, several challenges have been occurred in deep neural networks research. One such challenge is the labor-intensive process of annotation. Annotating large datasets is crucial for training deep neural networks, but requiring domain knowledge and time-consuming efforts. Another challenge lies in privacy-preserving techniques. As the amount of available training data increases, protecting the privacy of individuals captured in these images has emerged as a major concern. In addition to this, the construction of high-performance deep neural networks requires large amounts of image data for training and powerful GPUs for computational demands. The design of neural networks has been relied on the expertise of human professionals. These experts possess extensive knowledge and experience in determining the most effective configurations, such as the number of layers, the inclusion of skipping connections, and the choice of activation functions, and so on. Furthermore, developing neural networks models requires significant computing resources. Training and evaluating these models can be a time-consuming process, often taking several tens of hours or more. Given these factors, the question arises, can we automatically design the optimal neural networks? In recent years, neural architecture search has been the focus of much attention. Neural architecture search is an automated approach that aims to find high-performance neural network architectures, even for unseen data. By automatically designing the networks, neural architecture search eliminates the need for manual architecture engineering, reducing time and effort in the design process. Neural architecture search accelerates the search for optimal architectures and promotes innovation in neural network design. While neural architecture search primarily focuses on the exploration of model architectures, it raises the question of whether we can also extend the search space to encompass the training dataset. For image dataset constructions, human involvement is important, often requiring considerable time, effort, and also domain expertise. For example, the ImageNet dataset with 14 million images across 21,000 categories took over 2 years, and the efforts of approximately 50,000 annotators. However, these large datasets pose ethical issues, including privacy concerns and potential biases related to age or sex. Measures like limiting image usage to academic purpose aim to address these issues, but the need for continuous improvements in privacy protection and bias elimination remains crucial. Many state-of-the-art models utilize pre-training on large datasets like ImageNet. However, more and more high-scale datasets than ImageNet have been proposed. The JFT dataset developed by Google and the IG dataset by Meta are approximately some 100 times larger than ImageNet. This substantial increase in data size significantly enhances the representation and performance of image-based models. The availability of these large-scale datasets has proven beneficial for both convolutional neural networks and vision transformer models during the pre-training phase. Also, ethical issues have emerged in image datasets used for computer vision, raising concerns regarding fairness and transparency. One prominent issue is the presence of offensive labels within these datasets. For example, the dataset called ATM Tiny Images contained offensive labels leading to its suspension from public access. Another ethical concern is the dataset bias. Even in widely used datasets like ImageNet, the bias emerged in terms of gender and races as concern categories exhibit skewed distributions that can perpetuate unfairness. Transparency is another important aspect to consider. For instance, there have been estimates that approximately 6% of labels in ImageNet concern errors. These labels errors can affect the integrity and reliability of the dataset, impacting the training and the evaluation of models. To address these issues surrounding AI ethics, copyright and annotation labor, formula-driven supervised learning, FDSL, was proposed. FDSL, similar in framework to self-supervised learning, is designed to generate synthetic images without need for natural images taken by a camera or a simulation environment. Instead, this approach employs simple mathematical formulas and functions to simultaneously and automatically generate synthetic images, patterns, and their corresponding levels. This innovation aids in pre-training image representation, reducing the dependency of conventional data source and labor-intensive process. This formula-driven supervised learning has seen significant developments in various domains. In the spatial domain, methods like video pairing noise have emerged, while in the 3D domain, techniques such as multi-viewpoint and point clouds have become notable. As for the recent work similar to our approach, Task 2 Sim, which focused on finding the optimal synthetic image representation for downstream tasks. This is accomplished by predicting simulation parameters based on Task 2 deck embeddings on downstream tasks. The results are promising, with the recognition performance equivalent to ImageNet pre-training models in some cases. However, the work is not without its limitation. The search space for synthetic image representation remains limited, and the current models do not fully consider dataset configuration, including factors such as category or intra-category variation and dataset size.
Thank you, Shimura-san. From this point, I will do presentation. My name is Yosuke Yamada. In our work, we are going beyond the realms of neural architecture search, where the focus has been primarily on finding the optimal relationships as architecture and dataset for peak performance. We present the concept of neural dataset search, a process aimed at exploring the most effective pre-training datasets and architecture configuration to enhance pre-training outcomes. Our goal of neural data search is to search the best parameters within a pre-training datasets, given a specific architecture and downstream task. For instance, in neural dataset search, the search space becomes pre-trained datasets generated through something laws. While on the other hand, in neural architecture search, the search space is different neural architectures. Therefore, by simulating each of them with the search space and finding their optimal combination, we consider that we can efficiently produce the best combination of pre-training data sets and network architecture for various downstream tasks. So the interplay between neural architecture search and neural dataset search brings a fresh perspective on achieving higher performance in pre-training. Yeah, in our research, we demonstrate the potential of neural dataset search. Specifically, we leverage fractal database in the datasets emblematic of formula-driven supervised learning. The goal is to assess the performance of various fine-tuning techniques across the spectrums of generation parameter and diverse various resonance models. Our approach involves using fractal database and its assessment of generation parameters. This allows us to evaluate the impact of this variable on the fine-tuning performance when combined with different resonance model. Yeah, this slide shows the fractal database construction. Fractal database is in order to make a pre-trained model without any natural images. In order to automatically generate fractal images, we use iterated function system. The function consists of transform function and affine transformation. Iterative function system iteratively renders a large number of dots or patches in fractal images based on these two different equations. Fractal database is randomly search categories and conduct a simple sanity check whether a fractal category is remaining or not. At the beginning, we render a fractal image with randomized parameters through iterated function system. If the filling rate is over the threshold, adding the fractal category into fractal database. We iterate up to define number of category. In this case, parameter separation makes a different category. Instance augmentation of fractal database through these techniques. The iterated function system weight, rotation, and random patch drawing. Iterated function system weights varies fractal images by tweaking parameters. Rotation performed 4 times in 90-degree steps minus standard image rotation. Random patch rendering replace pixel points with random patches. We generate 1,000 instances per category in fractal database by combining 25 iterated function system weight for rotation pattern and 10 random patch drawing pattern. Well, let's get into our experiments. We conducted 3 different experiments. We kicked off with ImageNet, pre-training, or LASNet. Next, we divided into the nitty-gritty of how fractal images are represented. And finally, we explored how the configuration of fractal database and architecture size in this, specifically to evaluate the potential of fractal database in context of neural dataset search. We conducted pre-training of various resonant models. During pre-training, we modified the configuration of fractal database and adjusted the model architecture simulatory. Following the pressuring phase, we fine-tuned the resonant model on various downstream natural images datasets to assess its effectiveness. Recently, the vision transformer has also been validated. However, in this experiment, we focus on CNN model resonance only from a computational point of view, since the experiments are exploratory on a large pressuring dataset. First, this experiment direct our attention to the performance of resonant architecture and the ImageNet pre-training conditions. Our findings show a decline in identification performance at the architecture size, increases for both the learning from Scratch and ImageNet 100 pre-trained models. This outcome implies that the pre-training effect might be less noticeable at the architecture size grows unless the pre-trained dataset suppress a specific size. This experiment focus on two crucial image representation parameters with structured database, image size, and iterated function system weights. Instance augmentation allows to fine-tune the shape of our structured images. So we discovered that the variation in these shapes significantly impacts pre-training effectiveness. Image size also came under our microscope intensively. Smaller fractal images outperformed their large fractal images in pre-training, with a considerable performance gap observed in the food 101 datasets. Our experiment highlights the necessary to optimize image representation parameters in fractal database for effective pre-training. In this experiment, we set out to examine how alternation in the parameters of fractal database, specifically the category and instance counts, would influence their fine-tuning performance. To ensure a robust investigation, we conducted our experiment using 3 variations of the resonant model. Our findings revealed that the performance of fine-tuning exhibit distinct differences based on the category number and the instance count of fractal DB. As you can see from the graph, there's a notable distinction in the category number required to achieve sufficient pre-training effectiveness across different resonant models. For instance, resonant 18 and resonant 34 required a certain number of categories for optimal performance. However, for resonant 50, the number of categories needed for similar effectiveness was different. This severity emphasized not only the role of category count in pre-training, but also the importance of considering the specific architecture in use when configuration the dataset. Conclusion, our study outcomes have eliminated aspects of synthetic pre-training, particularly in relation to dataset and architecture changes. In our experiments with ResNet 50, we found that the pre-training effectiveness of fractal database varieties significantly when all tuning generated automatically generation parameters such as the method of instance generation and image size. Furthermore, we determined that as the architecture size increases, the number of categories required in fractal DB also escalates. Furthermore, we determined, however, our model most virtual insight came from observing variation in pre-training effectiveness. This variation led us to key realization. For synthetic pre-training, there exists optimal set of parameters that is cognate on the relationship with the architecture. In conclusion, our findings underscore the value in passing these optimal parameters for pre-training. This significant insight moves us one step closer to our goals. Thank you so much.
So if I understood correctly, the fractals you retrained on, they all seem to be just monochrome images.
It's not monochrome.
Or was that just the slides that you had there that showed them as monochrome? Right, okay, so in general, they are full color images.
Yes, our fractal DB doesn't contain the color because we also conduct some research, colored or non-colored.
Yeah.
And the non-colored one is actually more better performance.
All right.
Yeah, I think we understood that because if we colorize them, I mean, sometimes models learn like the category for just as color.
Yeah,
So,
pre-training tasks so it's
right.
easy. Optimize pre-training tasks difficult.
Brilliant, brilliant. Any further questions from anybody?
You've done a lot of like work in a lot of experiments on ResNet 50 or in the ResNet. So I'm trying using that to see what you're doing data generation, we try doing architecture search to see something work together.
I mean, like a big like a big or other.
I was just a lot of the experiments we've done ResNet 50.
Yeah.
Have you tried to generate automatically the architecture rather than using predefined ones?
Yeah.
Yeah, we agree with that opinion. I mean, just as our title, we just exploring the potential of the data set and but our final goal is like generate all this and the data sets simultaneously.
And transform our base model and share base model we try.
Yeah, but the computational resources and we didn't conduct it. But that's maybe interesting.
Brilliant. Any final questions from anybody? In which case, thank you very much.
Okay, so next up we have Lottie Hendricks, and I'll set this up for you.
Hi everyone, good afternoon. My name is Lotte Hendricks. I belong to the University of Leuven, and together with our colleagues working on AI accelerators, we conducted work on hardware-aware neural architecture search by genetic optimization with a design space exploration simulator. A short outline of this presentation. First, I will give you a short introduction, then I'll go into detail on our methodology. I'll show you our implementation, and then finally, the most important part, obviously, the results. So what do we understand by hardware-aware neural architecture search? The idea is obviously automatically generating the best architecture for a given data set and hardware in our case. But what does hardware-aware mean? Everyone who's conducted experiments on this uses a different approach. So we've kind of made this little summary on the various strategies that have been used in the past. The first one is maybe a bit more simply put, no physical hardware used. So you could use something like multiply accumulates or floating point operations or model size, which are more like things that belong to your neural network. So you don't need any hardware for this, but it does give you a good idea on if something is very intensive or not. Like something is a big model size, it's obviously going to need more compute resources than a very small model size. The most obvious solution is obviously just put your hardware in the loop, and then you can obtain latency or energy, but then you do need the physical hardware as well as generally the tool chain that will go with it. So compilers, etc. It might not be that easy to implement, as well as the hardware in the loop approach is obviously sometimes quite time consuming. You could use a lookup table, which you have to build. So you do need to conduct a lot of experiments to obtain a table, and then you can also use latency or energy. A fourth option that people have been using is using a prediction model. So build a neural network, train it to give you predictions, and then you can use that. But then again, you need a lot of data to be able to do that. Some people have used other machine learning models, such as random forests. And the last one we've kind of found out is what we call rough analysis. People look at the neural network and then get a result for latency or energy by kind of doing some computations and then adding some compensation factors that they kind of roughly determine just kind of by hand because they've got experience with it, and then they compensate and get a result. So it's an analysis, but there is like a rough feel to it. So we looked a bit further into hardware performance modeling, because on one side you've got neural networks, and on the other hand you've got hardware for neural networks. And there is obviously the people who make the neural networks and the people on the other side that design the hardware. They don't always know the intricacies of designing a neural network. They know very well how to implement it on hardware, but they don't really know how to design good neural networks. And the opposite is probably, in my case, true for hardware. I do understand a little bit about it, but I can't build a chip. So these people on the hardware design fields, they have actually started creating tools to model their ASICs and stuff like that, because building chips is very expensive. So they needed good tools to get ideas about their performance. That's what they call a design space exploration framework. So they build tools that can give you ideas about how well your neural network will perform on different types of hardware, but also how to map it on a certain type of hardware. So you can get a very good idea on how good that type would be. But they don't really use it for like getting ideas about neural networks. It's just for them to see how good is our chip. So we got the idea to kind of combine our work. And the one we've chosen is obviously the one from our colleagues. It's called Zigzag, which has a few advantages, obviously. They provide a lot of hardware descriptions already for TPUs, NPUs. But on the other hand, you can also quite easily give your own model to the system, because other frameworks, they generally really need a very detailed hardware description, which this does not really need. They've also got a very advanced latency modeling. They really look at all the different memory levels you have, the caching possibilities, the bandwidth, all stuff like that, which is very important. But as neural network designers, you don't really got a clue about that. And then lastly, we've helped them implement ONNX interfacing. Why everyone who's ever designed neural networks or worked with them is you've got so many frameworks, and then you need to put things together and then it doesn't work. So we chosen to work with ONNX since it's compatible with frameworks like PyTorch or TensorFlow. but it does need a little bit of work to make it work with other frameworks. So we helped them with that. A short overview of our approach. We use NAS strategy, an existing one. Why there's already been so many made, why design a new one? Then we export to NNX. We put it into the zigzag framework, which needs a hardware description and a mapping. So in one way, what does the hardware look like, which could be like your NPU or something like that, and also how to put the workload on it. Then we get a detailed performance back, and we feed that back. So we used NSGA-NAT. It's been around for a few years. It's based on the NSGA2 method. It's an evolutionary approach. In the past, we've worked on hot starting with MobileNet v2. Why also in the hardware world, they seem to really like using MobileNet v2 because of the depth-wise separable convolutions, which is for chip designers and scheduling people quite complicated to implement. And then we've obviously worked on that PyTorch and ONNX compatibility in the past. So we've also been doing multi-objective NAS with zigzag. I think most people do multi-objective neural architecture sets lately. Zigzag provides us a very detailed breakdown of the execution of a neural network on a specific device, and we focus on then taking the latency or the energy and test accuracy for the multi-objective optimization part. So here is a little snippet of what that zigzag tool gives us as an output. It's a JSON file. This is the energy snippet. At the top, you can see the energy total, which is the metric we've been using for energy, but you can also see a breakdown of what is the operational energy and how much goes to memory. So you can see, I think most people know that already memory is the big bottleneck in it. It's not really the execution, it really is that. And if you want to know more, you can also go into it with the levels of memory and the activations or the outputs, the inputs. So if you wanted to, you could really focus on very specific things if you were noticing a bottleneck with something. Then also very important, the data set. We work a lot on task-specific stuff in our research group, and research for us has shown that less diversity in a data set leads to smaller networks. For example, like in pruning, you can prune a lot away on very task-specific data sets. So we do a comparison between what we call the sunflower data set. It's a data set of small images, 32 by 32, that has a goal of being able to navigate with a drone. So the picture says right, left, top, bottom, so you can navigate on that. And we compare it to Cypher10, why there were also very little images. We thought that was a fair comparison. Most importantly, obviously, what are the results of these experiments? These are the results for our sunflower optimization experiments. On the left, you can see the results for optimization for latency and accuracy, on the right for energy and accuracy, and then obviously for the 5 types of hardware provided. Generation 1 is indicated with the little square, and those are average results of the population. And then the triangles indicate generation 40. So some interesting things we see is that at the start, the accuracy is very low. We're not able to really leverage the mobile net in this case. At the end, though, the accuracy does rise by kind of making the network smaller. The accuracy rises, as well as we're obviously able to reduce latency and energy consumption. These are the same results within a table. So if you look at that in generation 1 and generation 40, I'll put here, and then we've calculated the reduction factor. So the MPU, I would say, is our winner. We were able to reduce the network basically by 4.85 for energy, and then for latency 4.68. Not all of them perform as well, which is also kind of to be expected. These accelerators are built very differently, because what are the differences? Some of them have lots of memory available in different levels. Some have a lot of execution units, so your calculation thing, but not so much memory, so not that easy to schedule on. So you can also see that for certain tasks, certain accelerators are much preferable if you can't be able to build a task-specific ASIC. Then we did some results on Cypher10, also for the MPU, why the MPU was our winner. So we wanted to see what the results on Cypher10 would be. The first thing we really noticed is that the accuracy is immediately good. In generation 1, you've got a good good accuracy. It's only trained for 20 epochs. It's early stopping, so results could probably be better, but we see where we were barely able to reach 20% accuracy for the sunflower data set because the network was way too big. That's not the case in this case. What's also very noticeable is that, especially for the latency, so the red dots on the left, we see that we are basically dropping in accuracy by reducing. The first few generations, we're able to reduce in latency cycles or in energy, but by the time we reach generation 40, our network has become smaller, but we're losing in accuracy, which is obviously not really what we want. We still want to remain good in accuracy and good in our chosen metric. So our conclusions for this were that our NAS approach can definitely help with reducing both latency and energy consumption. That in the most optimal case, we are able to reduce the mobile NetV2 model up to 4.85 times for the specific data set without a drop in accuracy. And also for people who work a lot with different hardware types, that some hardware types are definitely able to achieve higher reduction rates than others, which goes to show that you can't just use whatever you want in certain cases if you want the most optimal results. So then I thank you for your attention, and if there's any questions. Yes.
So suppose it use hardware emulation like does like the library things that change anything?
Sorry?
If you do hardware emulation.
Yeah.
So like will the library account for that?
Sorry?
If you do like hardware emulation,
yeah,
you run like the DSC on it, like will it also account for the simulation by like the emulation?
Or do you mean that there is maybe a little bit of a discrepancy between the results from the simulator and real results?
Yeah, so for example, you run the operation on a normal network, so running towards let's say you're running on set and you kind of use hardware itself, so you have like a time shared version of that. Will it also account for
Well, this is really based on real TPUs, stuff like that. But I guess because you can redefine the hardware setup, you're probably able to account for that. Yeah.
So it was not clear to me what kind of transformations you did in the network. So you started mobile net V2 as your base network.
Yeah.
And then what happens to the network? I didn't see what was your.
It's really the same thing as the NSGA net. So you basically change your convolutions. You can add more or less convolutions, stuff like that.
And you did also perform like pruning and quantization at the end.
Quantization, yes.
But not pruning.
No pruning. No, we saw that as because NSGA, it has this idea that you're already taking in stuff and you're already taking out stuff. But yeah, indeed, the
so you
quantization.
assume by the process of choosing the convolution,
yes,
you already automatically prune. Did you end up with a lot of depth-wise convolutions at the end?
Yeah, many stayed actually, because the hardware is actually able to take care of it quite well.
And for all the hardware is the same?
I don't think we've checked all of them, but the results for hardware are actually quite different, which is one of the things we really notice. Different types of hardware like different things, if you can put it that way.
Exactly.
They're peculiar like that. Like
because you were saying that depth-size convolutions are difficult to implement. They are not difficult to implement. They are just very efficient in parallelism.
The people from the hardware fields would say they are difficult for them
because we are always complaining about depth-size convolutions, but it's because we cannot parallelize them efficiently.
Indeed, that's why. Yeah.
Any other questions? So I've got a question. So you've added zigzagging as effectively a way of defining whether a particular network would work well on that particular hardware. What sort of impact in terms of the training process?
Very little, actually. It's very efficient. The people who developed it, they worked very hard on making it efficient, and especially with the whole training pipeline of NAS. This is not that time intensive. Yeah. It really only adds a few seconds to it. Runs quite quickly.
Right. Any final questions? Go for it, go for it.
There's one thing, so you use mobile SV2 as
Yeah.
your base model. Did you try other models like mobile SV1? Because in my experience, mobile SV2 is the worst possible model for embedded platform.
Yeah, true. No, we stayed with the mobile net v2 because of that. We really wanted to focus on
But
on
it
it.
would be, if you compare mobile SV1,
Yeah.
you would have actually a comparison
Yeah.
of how much the technique affects and how much the basic design affects.
Yeah, that's true. Maybe in the future we will do that, but not for now.
Brilliant, thank you very much.
So our next speaker is, if I get the original slides back up. Next speaker is Yu Hao Chen. However, we have not had any word from him yet. There's no one in the room for that. I'll do one call. One last call is Yu Hao Chen. Is he in the Zoom?
There's only 3 people in the room. Yeah, that's me.
Oh, perfect. Okay, so how do you want to get your slides?
I can use my laptop.
Might be quicker to email, so if you can just. I'll just get everything else set up. So we're just going to hopefully get set up quickly. Should not be too much longer.
Whilst they're sorting that out, I'm going to do my usual plug to get people. I'm sure you're sick of this by now. Is there none before that?
There is, but the way it's set up didn't transition properly. It tries to force itself to the next slide on the previous slide.
Let's get forward though.
If you want. Haven't got through yet, I think.
Yeah, so as I say, we need evidence for our sponsors that we're actually getting people to attend the workshop. So the online form there, or there's a paper version of the form there. If you haven't signed up already, I think pretty much everybody has already. And if you want to join our mailing list, that'd be great.
Which one is it? This one? I think it should be working. Yeah. Okay.
Hello, everyone. My name is Yu Hao Chen, and I'm from University of Waterloo Vision and Image Processing Lab. And this is a work done by the collaboration between our lab and Darwin AI in Canada. So welcome to my talk on GraphNext, a fast self-attention neural network architecture for multitask learning in computer vision tasks for robotic grasping on the edge. So in robotic grasping, it is quite important for the network to be able to handle a lot of different tasks. So some typical tasks, including segmentation and object detection, try to help localize the object. And then some other tasks such as post-estimation, object center of mass detection will help the network, help the robots to determine, to understand the environment, the scene, to make sure that the grasping can be applied precisely and then doesn't really cause any damage. So in this particular study, we focus on 4 different tasks for a robot arm, which is object detection and segmentation, center of mass prediction, and suction heat map prediction. So later on, we also include another task, which is A-model segmentation, which basically look at the object, even though predict object mask, even though the object is occluded, and then determine if there's any occlusion with it. So our goal is to develop a more efficient network architecture instead of the high architectural and computation complex architecture that is used initially in the current, most of the current multitask learning framework done by a lot of the latest object A-model segmentation network. So the goal for our network architecture search is that we want to come up with a optimization strategy using generative synthesis to find the optimal architecture. So this is the optimization problem that we define. Basically, we want to find the best network, let G to be the network generator. We want to generate networks such that it maximizes the network performance on a given performance measure U, and then where it is subject to the constraint provided by the indicator function. So this constraint optimization problem is iteratively solved using a collaboration between a generator G and then inquisitor I. So the whole process is actually done in another work, but we are leveraging this work for generating our problem. And then our goal is to achieve the desired balance between network accuracy, architectural complexity, and computational complexity as well. And then for the design constraints, basically we want to make sure that the network is able to implement anti-aliasing downsampling to enhance the network stability as well as robustness. And then second, we use the attention condenser, which is highly efficient self-attention mechanism designed to learn condensed embedding characteristic joints, characterizing joints, local and cross-channel activation relationship for selective attention. So basically, this attention condenser is applies on the attention map and then try to encode the attention by using a structure similar to a autoencoder. And then lastly, we want to enforce a flop requirement for less than 300 billion flops with an accuracy requirement with no lower average precision across all the tasks than the ResNet 50 variant by 0.5%. So this is our end architecture that is generated and then proposed by our work. So basically basically, this architecture possesses a self-attention neural network architecture with highly optimized macro architecture and micro architecture designs for all its components. And the network architecture here has the constraint, are within the constraint that we imposed. And then the generated backbone architecture are feeding to a next generated feature pyramid network that is also generated by our optimization problem. At the same time, we also optimize the network with respect to each head, the performance of each head architecture. And this is a multitask training loss that we use. So as you can see that it performs a lot of, it includes a lot of different losses. For each loss is designed for each task, and then we use a set of weights to weigh each of the tasks. And then this weight is, we obtain the weights empirically, and there has been fixing the weights throughout the network search. So here are some preliminary, here are some results when we apply our data, our network architecture onto the latest grasping data set, which is MetaGraphNet benchmark data set. And then we also compare several state-of-the-art efficient backbones with our multitask network architecture. And then we evaluate all the network architecture on NVIDIA Jetson TX2 embedded processor. So basically, our network architecture is able to provide a 3.15 times inference compared to the ResNet, and then also compared to efficient net and the mobile net. Our network is also be able to provide more than 2 times faster performance. And then throughout the category of all the tasks, we are able to outperform other networking in the average precision as well as the heat map mean square error estimation. And then finally, our network is much smaller, which is 5 times smaller than the ResNet counterparts. And then here are some visual results. So you can see that the network prediction is fairly accurate on this data set. And then on the right side, it's the center of mass prediction as well as the suction grasp heat map prediction. And then those are the rest of the result. So in particular, you can see that our network still performs quite well in the A model segmentation as well, which predicts the mask is even though that it is occluded. And thank you. That's our presentation. Any questions?
Any questions?
I have one, which is generate network from this hardware. So the problem overcoming, I think is like I mean, in the benchmark, the model is audio architecture. Some work based on some models, some work based on other hardware. What's the reason for that?
I think one of the reasons can be just not everyone has access to the same hardware, or like it's costly to always purchase the newest hardware models every time when you want to evaluate. Yeah, so like for cloud-based, you can evaluate your performance on cloud computing, and you can select different GPUs to use. But for hardware, you purchased it, and then it's difficult to set it up in the first place. And then And then it's costly to buy a new set of hardware just to measure. And sometimes for the latency study, hardware provides a lot more variance in terms of the latency measurement. It's not as stable as the typical like the typical tower case PCs. I think that's the reason that everyone evaluate on different ones. Okay. Thank you.
Any final questions? Chris, thank you very much.
Thank you. And then I can.
So we do have 2 papers left. The next paper though is somebody coming in from China, and it's quite early in the morning there. We told them what would it be, 4:45 for their paper, so we're a little bit ahead on that. But is anybody here from the final paper?
It should be fine.
Because we hadn't actually heard anything from the authors of the final paper.
I do not know what's using it.
We're hoping that we were just going to be here on the day, but
it's just trying
to. Is it this one?
Nobody's
Is
there.
That's
I
mine.
think we're going to have to wait,
That's weird.
unfortunately.
Okay, I will just
to see
upload
if this
it.
other person turns up for
Thanks.
their presentation. Yeah, so I can do a dance in front of you if you want, but we're going to have to just hang on a few minutes to see if this other person turns up, and then see if anybody turns up for the final paper slot.
so it's currently Q2. So this is when we expected Yongguo to appear. And do see that someone has joined the chat. Are you part of paper 7 or paper 8? So either part of Yongguo or Luban Lee's team.
Hello, sorry, how to share my screen?
So which paper are you for? Are you for Yongguo?
I'm in the second author. Yeah, I had to replace Yongguo to share
Okay,
the slides.
Perfect. I think you should be able to do that if I stop sharing. You should.
Okay, I find it buttoned. So could you see the slides?
I think so. Yeah. Okay.
Okay. So hello everyone. Today I'm going to share the paper accepted by the CVPR workshop. The title is Pareto-Aware Neural Architectures Generation for Diverse Computation Budget. So I will briefly introduce the background and then introduce our method, the PAG, the Pareto architecture generation, and then I will show some results. So in deep learning, when we decide effective architecture, we often relied on the human experts, and we need to spend great of time and effort on it. And in about 2017, neural architecture search was proposed to automatically decide the architecture. But in practice, we have to carefully decide architecture to satisfy some computational budget, like the latency or the memory usage. So we have, furthermore, we have to consider more or various computational budgets in the real application. When we developed a deep learning application, we made deployed application in different mobile phone. So in this case, we want to develop various architecture to satisfy different computational budget. So currently, most NAS method only consider a single budget and incorporate the computational cost in the objective. So when we consider more the budget, the NAS method has to conduct more than one search process for each budget. So it's very efficient and maybe unnecessary. So our question is how to decide effective architecture on the diverse or different budget in an efficient way. So this is the motivation of our method. So we seek to direct or devise an architecture generator that only we need to train once, and then it will generate the Pareto optimal architecture for different budgets, varied inference. So you can see the left figure. And to achieve this, we seek to learn the Pareto frontier instead of finding a single optimal architecture. The illustration is in the right figure. So next, we go deep in our method. So here is an overview of our method. So in the left down corner, we have a architecture generator. So it seeks to evaluate an architecture under a specific computational budget, such as we want to For example, we want to evaluate architecture performance under a latency of 100 microseconds. In here, we devise the architecture generator. So the input of this architecture generator is B. So B is the computational budget, such as latency. And the theta is the parameter of this generator. So it will output an architecture under this computational budget B, like this. And then we will put this architecture effort into the evaluator, and it will output the performance or the scoring of this architecture, whether the case is good or have poor performance. And the generator will regard it as the reward R, and then we will change the generator via reinforcement learning, such as policy gradient algorithm. So that's the overview of our method. For next, we want to start with a new architecture search under a single budget. So under a single budget, one can learn the policy pipe via the reinforcement learning. And the popular way is to sampling a lot of architecture from the policy and then maximize the expectation of the reward, usually a combination of the performance like accuracy and latency. So here B, we use B to denote the budget, such as latency, and we use pi to denote the learn the policy, and we use R to denote the reward function or the reward. That's consider performance and accuracy. That's considered both the accuracy and latency. So when we consider diverse budget, we want to learn an approximate a Pareto frontier by finding a set of the architecture. So to do this, we eventually sample K budget from a range of latency and then maximize the expectation. So the difference is from the above equation is we have two expectations here. The inner one is the same as above one, and in the outer, we have another expectation on the budget. So except for this, they are almost the same. So here another question is how to represent the budget. So in practice, we represent the budget as a vector. So since we eventually sample K budget here. So this K budget is we represent them with a learnable embedding. For the budget between them, we use a simple linear interpolation to represent it. To represent it, we use the following equation. So we just simply linearly combine the B1 and the B2 to represent another computational cost speed between them. So in the experimental result, we will show this proposed vector represent method is good for performance. So next, we move to learning the evaluator. So just now we mentioned, we introduced how the architecture generator works, and then here we want to introduce the evaluator. So the input of architecture evaluator is architecture beta and budget B. So we want to predict the performance or scoring of this architecture under budget B. So this here is a case that's given an architecture, the scoring will be different if we give it a different B. So we trained this evaluator with a ranking loss. We use a M architecture, but with accuracy and latency. Yeah, and here we use a ranking loss in equation 4 to update the evaluator. Use gradient descent. So here is a D, the denoted function that indicate whether one architecture is better. So the final question of our proposed method is how to recognize which architecture is better between two given architectures. So here we have devised a Pareto dominance rule to do this. So we have two architecture. The one is beta 1, another one is beta 2. And given these two architecture, we design the following the rule. So it actually is the function D that mentioned here. So the equation 5 looks a little complicated, but the nature of this function is very simple. So the function D equal to 1, when it equal to 1, we think beta 1 is good than beta 2. When it's equal to -1, we think beta 1 is not better than architecture beta 2. So in the case 1, when both this architecture satisfy the computational budget, we think the architecture with better accuracy will lead to high scoring. So this case, this function is equal to 1. So when one architecture is satisfied and another is not satisfied, so here the beta 1 is satisfies and the beta 2 does not satisfy. So here we think that the beta 1 is not good than the beta 2. So in the third case, when the beta 1 has a lower computational budget, so here we think the beta 1 is good than beta 2. So in the last case, when both two architecture does not satisfy the budget, we think the beta 1 is not good than beta 2. So here I will show you some experimental results. So in the paper, we indeed conduct the experiment on 3 different devices, including the mobile device, SQ here, and the CPU device and GPU device. And we compare the latency and the test accuracy on the ImageNet. So we group this architecture according to their latency. Then, and in this table, we can find that the architecture generated by our PAG method outperform the existing one when they have the similar latency. And here we show some visualization of our method. So in the left figure is about in the left figure, we can draw the same conclusion as the above table. In the right part, we generate a lot of architecture that their latency is from 80 microseconds to 200. And we found the Pareto frontier generated by our method PAG is better than another method use the multi-objective. And this is another experiment. So in the figure 8 is the ground truth latency histogram. So we the max latency of sample architecture is about 200 or 210, and the minimized one is about 80. So the architecture generated by our PNG, the most generated architecture is less than 110. So it's the 110 is the given the latency. So in this case, we always want to generate the architecture is less than this. So another method use the multi-objective. So it only generates a small part architecture that satisfies this budget, and most of architecture do not satisfy that. Here is another comparison. So here we compress the search time cost. In the introduction of our method, we say that when we have a diverse budget, we use the traditional NAS method to search for architecture with different budgets. We may need to perform the single or separate search process for multiple times, but our PNAG just train once and then generates in very short time via inference. So here we give some accurate number here. We generate architecture just less than 1 second, and the other NAS method always about several hours or even several days. So the last part is the conclusion. So in this paper, we propose PNAG that's only trained once and then can generate effective and proposing architecture for the given budget via inference for a very short time. And to train our PNAG, we learn the Pareto frontier by maximizing the reward over diverse budget. This is the difference between our method and traditional NAS method. So we also trained an evaluator and devised the Pareto dominance rule to recognize which architecture is better under a given budget. So here is my presentation, and if you have any questions, feel free to ask me.
Brilliant, thank you very much. Do we have any questions? I can start off with one. So in terms of your generation process, you're generating candidates that you think would be close to the Pareto front. How good were those predictions? Sorry, did you hear me?
So the question I didn't follow you. How good is the candidate architecture or what?
Yes, so you said on one of the previous slides that P9 predicts potential candidates for the Pareto front. How good were those predictions?
So how good are the candidate architecture?
Yeah.
So here we sample this architecture based on the learned policy, and our policy can generate the architecture based on the given input computational budget. But I'm not exactly know the question how good the candidate architecture. So do you mean the performance or accuracy of search architecture?
Well, I mean, you were talking about accuracy and latency. So they're the two metrics you're using here, aren't they?
Yeah, we use accuracy and latency.
So did these values that did these networks you predicted, were they where you expected them to be on that Pareto front, or you know?
So your question is how can we accurately evaluate this architecture?
Yeah.
So I will give you more detailed. When we evaluate this architecture, we use evaluator here, and indeed we need to sample a lot of architecture offline and get their accuracy and budget via some method like sharing method or another method to get accuracy, and we need to test its true latency on the target device. So the number of these sampled architecture for train the evaluator is about 16,000 in our paper. So based on this sampled data set, we call the architecture data set. So we use the ranking loss to train the evaluator. So after training, it will have a ability to indicate which architecture is better than another one.
Yeah. Okay, do we have any other questions? In which case, thank you very much.
Okay, so if you stop him sharing your screen. I think I can just take control. Actually. There we go. Where's my mouse gone? Thank you. So thanks once again. Get my Zoom meeting. It's over here. So I'm just going to share my screen again. So yeah, this is a final call for Lu Junli, or anyone who's part of their team, paper 8. Is anyone here with their team? Okay, should we then?
I think because I mean it is into the time in their paper. So, yeah.
So since we haven't heard anything back from them, we will assume that they are not attending. If they do get back to us at a later date and they provide a video, hopefully we should, when we get in contact with the person who manages the CVPR version of our website, we should be able to get all the presentations on there. And if we get in contact with Illusion, we will put their work on there. So we'd like to thank everyone who's still here with us. We know it's late in the day. Thank you for attending. If you want to talk about NAS at any point during the workshop, not the workshop, but during the conference, me and Steve are going to be here for the entire time. So you can send us an email at either Steve McGough or d.towers2@ncl.ac.uk. You can also stay up to date with future competitions and workshops by signing up to our mailing list or completing the form, which will show interest. And so I'm going to leave this on until everyone has left, but thanks again for attending and hope to see you next year.
Indeed, yes. Thank you all for being here. I think we've had some good papers today, and we will just hang around in case anybody does turn up for this final paper, or if anybody wants to ask any other questions about NAS. But thank you very much for your attention. Thank you for